Before we drift too deeply into the stellar twilight, may I gently inquire, from what quiet corner of our world are you listening tonight? And as the universe unfolds its secrets for us, what time does your clock whisper it to be? Welcome, my dear listener, to this quiet corner of the cosmic narrative. It's a true joy to have your company again, as we embark on another journey into the profound mysteries that weave through the universe, offering us a chance to simply, our purpose, as always, is to gently unfurl a story from the fabric of existence, a tale whispered by the stars themselves, guiding your thoughts to a place of wonder and perhaps profound rest. Tonight, we shall venture into the heart of an event so incredibly powerful, so intensely luminous, that it utterly redefines our understanding of cosmic might. We will trace the life and the ultimate, cataclysmic farewell of a star, not just any star, mind you, but one that chooses to depart in the most spectacular, most devastating, and yet strangely beautiful way possible through what we call a hypernova. Imagine a final brilliant sigh that reshapes galaxies, a cosmic crescendo echoing across unimaginable distances. You know, sometimes I find myself looking up at the night sky, and it almost feels like the stars are humming a secret song. Just for us, it's a vast, intricate melody, and tonight, we're going to listen to its loudest, most astonishing note. If you find a sense of peace in these explorations, if they offer a soft landing for your mind, then a quiet like or a gentle subscribe would be a truly appreciated gesture, helping these calming cosmic tales find their way to others who seek a tranquil journey into science. Now, take a slow, deep breath, my friend. Let your shoulders soften, allow your mind to quieten. We are about to embark on a journey beyond the familiar, into the heart of cosmic power. Settle in, for our story begins in the vast, serene silence of space. We begin by settling into the vast, silent canvas of space, where seemingly tranquil expanses hold unimaginable forces, yet our senses perceive only quietude. Imagine, if you will, floating adrift in the deepest reaches of the cosmos, far from the hum of Earth, far from the rush of any wind or the murmur of any ocean. What would you perceive? Most likely, an overwhelming stillness, a profound, almost sacred quietude, punctuated only by the distant, unwavering gleam of stars that have been burning for billions of years. This silence is often the first thing we imagine when we think of space, isn't it? An empty, tranquil void stretching out infinitely in all directions, a canvas of impenetrable black velvet sprinkled with diamonds. Our human senses, honed by life on a bustling planet wrapped in a noisy atmosphere, interpret this as utter peace. There is no air to carry sound waves, no medium for our ears to translate vibrations into the symphony of life we know so well. So, the universe, to our immediate perception, is a realm of ultimate quiet. And yet, this quietude, this perceived emptiness, is profoundly deceptive. It's like standing before a vast, ancient forest at dawn. To the casual eye, it seems dormant, still, perhaps only a gentle rustle of leaves. But beneath that tranquil surface, an intricate dance of life is unfolding. Sap rising in trees, roots seeking water, countless creatures stirring, breathing, living. So it is with the cosmos. That seemingly empty expanse is teeming with activity, with forces beyond our wildest terrestrial imaginings. Within that quiet dark, stars are being born in fiery nurseries, swirling clouds of gas and dust, collapsing under their own immense gravity, sparking into brilliant nuclear furnaces. Planets are forming, tiny specks of matter, slowly coalescing, gathering themselves into worlds, some rocky, some gaseous, all bound by the invisible threads of gravity. Galaxies, immense islands of billions upon billions of stars, are performing slow, majestic waltzes, their spiral arms unfurling like celestial dancers. And within those galaxies, individual stars are living out their epic lives, some blazing brightly for eons, others rushing through their existence in a magnificent, fleeting sprint. The very fabric of space-time, which seems so smooth and unyielding, is capable of bending and warping, folding and unfolding, stretched by the presence of colossal objects. creating gravitational wells that guide the dance of matter. Invisible forces, like the enigmatic dark matter and the pervasive dark energy, silently shape the large-scale structure of the universe, pulling and pushing, stretching and compressing, without ever uttering a sound that our ears could comprehend. These forces are immense, truly staggering in their power, capable of tearing apart entire stars or weaving together colossal galactic clusters. They sculpt the cosmos, driving its evolution, guiding its destiny, all within that profound, echoing silence. Consider the gentle, unwavering light from a distant galaxy, perhaps millions of light years away. That light, which reaches our eyes as a faint, almost shy twinkle, has traveled across vast stretches of this silent void, carrying with it the story of countless stars and untold eons. It has pierced through nebulae, navigated around black holes, and traversed the expanding fabric of the universe itself, all without a whisper. This quiet perseverance of light, this relentless journey across unimaginable distances, is a testament to the powerful yet silent engine that drives the universe. The silence is not an absence of activity. It is simply the natural state of a realm where sound, as we know it, has no place to exist. It forces us to engage with the cosmos in a different way, not through our ears, but through our eyes, our minds, and our deepest sense of wonder. It invites us to contemplate the immense, the powerful, the beautiful, without the distraction of noise, allowing us to truly listen, not with our ears, but with our souls, to the silent, magnificent hum of the universe at work. As we drift further into this quiet, let your mind become attuned to this cosmic paradox, profound stillness masking incredible energy. The silence isn't empty. It is pregnant with possibility, with forces on a scale that hums just beyond our perception, waiting to reveal themselves in ways both subtle and spectacularly dramatic. Now, with our minds attuned to the deceiving calm, let us begin to perceive the whispers. Beneath that blanket of cosmic quietude, there lies an unimaginable reservoir of energy, vast beyond our terrestrial comprehension. It's like observing a giant ancient glacier. It appears utterly motionless, a frozen colossus, yet within its depths, titanic forces are slowly, relentlessly at work, carving valleys, grinding mountains, shaping landscapes over millennia. Similarly, the universe, in its grand silent ballet, operates on scales of energy and time that dwarf anything we experience in our daily lives. These energies aren't noisy. They don't roar or rumble in a way we can hear. Instead, they manifest as fundamental forces, the relentless embrace of gravity, the furious dance of nuclear forces, the pervasive hum of electromagnetism. These are the hidden currents, the deep rivers of cosmic energy that flow silently through everything, shaping stars, forging elements, and governing the fate of galaxies. Consider, for a moment, the seemingly gentle glow of a star, any star, even our own sun. What appears as a calm, steady light is, in fact, the product of an ongoing, incredibly violent process. Nuclear fusion. In its core, immense pressure and staggering temperatures force atomic nuclei to merge, creating heavier elements and releasing colossal amounts of energy in the process. Each second, our sun converts millions of tons of matter into pure energy, radiating it outwards as light and heat. This is not an explosion in the traditional sense, not a sudden, uncontrolled burst. Rather, it is a sustained, contained fusion reaction, a continuous, silent detonation occurring at its heart. The energy unleashed is so vast that it takes hundreds of thousands of years for a single photon, a particle of light, to zigzag its way from the sun's core to its surface, before embarking on its 8-minute journey to Earth. This immense output of energy, responsible for sustaining life on our planet, is just one whisper of the hidden power of the cosmos. And what about gravity? This invisible force, so familiar yet so mysterious, operates across truly immense scales. It is gravity that pulls together scattered dust and gas to form stars and planets. It is gravity that binds billions of stars into magnificent galaxies. It is gravity that binds billions of stars into magnificent galaxies. It is gravity that orchestrates the collisions and mergers of these vast stellar islands, events that unfold over hundreds of millions of years, releasing energies that defy human imagination. When two galaxies spiral into each other, as our own Milky Way is destined to do with Andromeda in a few billion years, it's not a head-on crash in the way two cars might collide. Rather, it's a slow, gravitational embrace, a dance of tidal forces that stretches and reshapes both structures, flinging stars into new orbits and triggering bursts of star formation. The energy involved in such cosmic mergers is staggering, silently reshaping the very fabric of the galactic landscape. Then there are the more exotic whispers, like the enigmatic dark energy, which appears to be accelerating the expansion of the universe itself. This isn't an explosion, but a subtle, pervasive push, an unseen force that is slowly, yet relentlessly, stretching the cosmic canvas, pulling galaxies further and further apart. Its true nature remains one of the greatest mysteries in cosmology, a powerful, silent driver of the universe's ultimate destiny. All these forces, these immense reservoirs of energy, exist within that initial quietude we contemplated. They are not loud, not boisterous in our human perception. They are the deep, underlying currents, the immense forces that shape everything we see and don't see, operating with a silent majesty that hums just beneath the surface of our awareness. They are the prelude, the quiet and profound foundation upon which the most spectacular and dramatic events of the universe unfold, setting the stage for something truly profound, something rarely seen, something that will soon transform a gentle giant into the ultimate cosmic fireworks. We are not talking about a simple stellar demise, like a star peacefully exhausting its fuel and shrinking into a white dwarf, or even the familiar, brilliant burst of a standard supernova. No, a hypernova is something altogether more intense, more focused, more devastating. It is the cosmic equivalent of a single deafening clap of thunder from a sky that had only ever whispered. It is the universe clearing its throat with an incomparable roar. When a star, truly immense in its proportions, tens, even hundreds of times the mass of our own sun, reaches the end of its life, its death throes are unlike anything else. Its core, no longer able to resist the inward crush of its own titanic gravity, collapses with unimaginable speed, not merely shrinking, but imploding with such ferocity that it bounces back with a violence that defies earthly understanding. But here is where the hypernova sets itself apart. Instead of an outward-spreading spherical explosion, which is what we typically associate with a supernova, a hypernova channels its dying energy into two incredibly powerful, narrowly focused jets of matter and radiation, lasting forth from its poles at nearly the speed of light. Think of it not as a firework exploding in all directions, but as a colossal cosmic lighthouse beam, two searing shafts of pure energy piercing through the fabric of space. These jets are the signature of a hypernova, the telltale sign of a final, hyper-violent goodbye. They are the source of what we detect as gamma-ray bursts, the most energetic phenomena in the known universe. Flashes of light so intense that for a fleeting moment they can outshine entire galaxies. Having sensed the subtle hum of cosmic power hidden beneath the quiet, we now turn our gaze towards the most dramatic of these expressions, the ultimate grand finale for a star. A farewell so spectacular, it redefines the very meaning of explosion. We are speaking, of course, of cosmic death, yet in the universe, death is rarely an ending. More often it is a violent, necessary rebirth, a shattering that sows the seeds for future creation. And among these stellar swan songs, there is one that stands out, a crescendo of destruction and creation, the hypernova. Imagine, if you will, the slow, graceful dance of a star through its immense life, perhaps for millions of years tirelessly fusing elements in its core, radiating light and warmth. But for the most massive of these celestial giants, their lives are not destined to fade gently into the night. Instead, they are destined for a magnificent, terrifying, and utterly beautiful exit. This immense burst of energy is not just a destructive force. In a strange cosmic twist of fate, this unparalleled violence is also a profound act of creation. These explosions are responsible for forging and scattering many of the heavier elements, like gold, platinum, and uranium, that are essential building blocks for planets, for life itself. Without these spectacular stellar deaths, the universe would be a much simpler, less interesting place, devoid of the very materials that make up you, me, and everything around us. You know this. These explosions are responsible for forging and scattering many of the heavier elements, like gold, platinum, and uranium, that are essential building blocks for planets, for life itself. So as we prepare to dive deeper into the mechanics of this ultimate explosion, remember that it is a story of destruction, yes, but also of radical transformation, of a cosmic crescendo that echoes with both a terrifying finality and a promise of new beginnings. It is the universe's grandest, most violent farewell, forever etching its mark on the tapestry of existence, a truly profound and captivating event. Think of it like a gentle whisper in a vast, silent hall. Within these enormous clouds, there are always slight variations in density. Perhaps a distant supernova shockwave nudged a region, or simply the inherent quantum fluctuations of matter caused a tiny clump to become ever so slightly denser than its surroundings. Whatever the initial trigger, once a small region has accumulated just a little more mass, its gravitational pull subtly increases. And this is where the magic begins. That slightly denser clump begins to very, very gently, almost imperceptibly, draw in the surrounding gas and dust. It's a slow, patient accumulation, like building a cosmic snowball. As more and more material is drawn in, the clump grows, and as it grows, its gravitational pull strengthens, accelerating the process. It's a positive feedback loop, a slow, inevitable march towards concentration. To truly appreciate the ferocity of a hypernova, we must first understand the gentle, almost dreamlike beginnings of the stars themselves, those luminous behemoths that eventually meet such a dramatic end. Imagine, if you will, vast swirling clouds of gas and dust, stretching for light years across the emptiness of space. These aren't the neat, fluffy clouds we see drifting in our sky. These are immense, tenuous nebulae, cosmic nurseries composed primarily of hydrogen and helium, laced with microscopic grains of dust, the scattered remnants of long-dead stars. In these colossal, dark, and seemingly still clouds, the journey of a star quietly begins. There's no dramatic ignition, no sudden flash. Instead, it's a slow, almost imperceptible process, driven by the most fundamental force in the cosmos, gravity. Over vast stretches of time, perhaps hundreds of thousands, or even millions of years, this contracting clump of gas and dust grows larger and larger, becoming denser and hotter at its core. As the individual particles are pulled closer together, they collide more frequently and with greater energy, causing the temperature within the core to steadily rise. This contracting, warming mass is known as a protostar, a star in its infancy, still cloaked in the veil of the very cloud from which it was born. It's not yet a true star. It doesn't yet glow with its own internal nuclear fire. Instead, it radiates a dim, reddish light from the heat generated by its gravitational collapse. It's a moment of profound transformation, the universe slowly knitting together raw ingredients into something spectacular. To truly grasp the scale and intensity of a hypernova, it's helpful to first ground ourselves in the familiar. Let us turn our attention, gently, to our own sun, that brilliant golden orb that warms our days and nourishes all life on Earth. The sun is, in every sense, a star, a magnificent, glowing ball of superheated gas, a cosmic furnace tirelessly performing its work. It is, however, a rather average star in the grand cosmic scheme, a comfortable, middle-aged star that has been shining steadily for about 4.6 billion years and will continue to do so for another 5 billion years or so. Its steady, life-giving hum is a beacon in our local cosmic neighborhood, the very heart of our solar system. This gentle inward pull, this slow gathering of cosmic material, continues until a critical point is reached. The pressure and temperature within the protostar's core becomes so immense, so utterly staggering, that something extraordinary happens. Nuclear fusion ignites. The hydrogen atoms, squashed together under unfathomable pressure, and superheated to millions of degrees, begin to fuse, combining to form helium atoms. This process releases an enormous burst of energy, pushing outwards and finally counteracting the inward pull of gravity. At this precise moment, the star is truly born. It ceases its collapse and settles into a stable equilibrium, a delicate balance between the crushing force of gravity trying to pull it inward and the outward pressure generated by its nuclear furnace. This is the main sequence phase of a star's life, a period of sustained brilliant light and warmth, a beacon ignited from the dust and dreams of the cosmos. The Sun, our own star, has been in this stable phase for about 4.6 billion years, a testament to the powerful, yet subtle, forces that bring these majestic cosmic forges to life. From seemingly empty space, a star is born, glowing steadily, patiently, ready for its long journey. Welcome, my dear listener, to this quiet corner of the cosmic narrative. It's a true joy to have your company again, as we embark on another journey into the profound mysteries that weave through the universe, offering us a chance to simply, our purpose, as always, is to gently unfurl a story from the fabric of existence, a tale whispered by the stars themselves, guiding your thoughts to a place of wonder and perhaps profound rest. Tonight, we shall venture into the heart of an event so incredibly powerful, so intensely luminous, that it utterly redefines our understanding of cosmic might. We will trace the life and the ultimate, cataclysmic farewell of a star, not just any star, mind you, but one that chooses to depart in the most spectacular, most devastating, and yet strangely beautiful way possible through what we call a hypernova. Imagine a final brilliant sigh that reshapes galaxies, a cosmic crescendo echoing across unimaginable distances. Before we drift too deeply into the stellar twilight, may I gently inquire, from what quiet corner of our world are you listening tonight? And as the universe unfolds its secrets for us, what time does your clock whisper it to be? If you find a sense of peace in these explorations, if they offer a soft landing for your mind, then a quiet like or a gentle subscribe would be a truly appreciated gesture, helping these calming cosmic tales find their way to others who seek a tranquil journey into science. You know, sometimes I find myself looking up at the night sky, and it almost feels like the stars are humming a secret song. Just for us, it's a vast, intricate melody, and tonight we're going to listen to its loudest, most astonishing note. Now, take a slow, deep breath, my friend. Let your shoulders soften. Allow your mind to quieten. We are about to embark on a journey beyond the familiar, into the heart of cosmic power. Settle in, for our story begins in the vast, serene silence of space. We begin by settling into the vast, silent canvas of space, where seemingly tranquil expanses hold unimaginable forces, yet our senses perceive only quietude. Imagine, if you will, floating adrift in the deepest reaches of the cosmos, far from the hum of earth, far from the rush of any wind or the murmur of any ocean. What would you perceive? Most likely, an overwhelming stillness, a profound, almost sacred quietude, punctuated only by the distant, unwavering gleam of stars that have been burning for billions of years. This silence is often the first thing we imagine when we think of space, isn't it? An empty, tranquil void stretching out infinitely in all directions, a canvas of impenetrable black velvet sprinkled with diamonds. Our human senses, honed by life on a bustling planet wrapped in a noisy atmosphere, interpret this as utter peace. There is no air to carry sound waves, no medium for our ears to translate vibrations into the symphony of life we know so well. So, the universe, to our immediate perception, is a realm of ultimate quiet. And yet, this quietude, this perceived emptiness, is profoundly deceptive. It's like standing before a vast, ancient forest at dawn. To the casual eye, it seems dormant, still, perhaps only a gentle rustle of leaves. But beneath that tranquil surface, an intricate dance of life is unfolding. Sap rising in trees, roots seeking water, countless creatures stirring, breathing, living. So it is with the cosmos. That seemingly empty expanse is teeming with activity, with forces beyond our wildest terrestrial imaginings. Within that quiet dark, stars are being born in fiery nurseries, swirling clouds of gas and dust, collapsing under their own immense gravity, sparking into brilliant nuclear furnaces. Planets are forming, tiny specks of matter, slowly coalescing, gathering themselves into worlds, some rocky, some gaseous, all bound by the invisible threads of gravity. Galaxies, immense islands of billions upon billions of stars, are performing slow, majestic waltzes, their spiral arms unfurling like celestial dancers. And within those galaxies, individual stars are living out their epic lives, some blazing brightly for eons, others rushing through their existence in a magnificent, fleeting sprint. The very fabric of space-time, which seems so smooth and unyielding, is capable of bending and warping, folding and unfolding, stretched by the presence of colossal objects, creating gravitational wells that guide the dance of matter. Invisible forces, like the enigmatic dark matter and the pervasive dark energy, silently shape the large-scale structure of the universe, pulling and pushing, stretching and compressing, without ever uttering a sound that our ears could comprehend. These forces are immense, truly staggering in their power, capable of tearing apart entire stars or weaving together colossal galactic clusters. They sculpt the cosmos, driving its evolution, guiding its destiny, all within that profound, echoing silence. Consider the gentle, unwavering light from a distant galaxy, perhaps millions of light years away. That light, which reaches our eyes as a faint, almost shy twinkle, has traveled across vast stretches of this silent void, carrying with it the story of countless stars and untold eons. It has pierced through nebulae, navigated around black holes, and traversed the expanding fabric of the universe itself, all without a whisper. This quiet perseverance of light, this relentless journey across unimaginable distances, is a testament to the powerful yet silent engine that drives the universe. The silence is not an absence of activity. It is simply the natural state of a realm where sound, as we know it, has no place to exist. It forces us to engage with the cosmos in a different way, not through our ears, but through our eyes, our minds, and our deepest sense of wonder. It invites us to contemplate the immense, the powerful, the beautiful, without the distraction of noise, allowing us to truly listen, not with our ears, but with our souls, to the silent, magnificent hum of the universe at work. As we drift further into this quiet, let your mind become attuned to this cosmic paradox, profound stillness masking incredible energy. The silence isn't empty. It is pregnant with possibility, with forces on a scale that hums just beyond our perception, waiting to reveal themselves in ways both subtle and spectacularly dramatic. Now, with our minds attuned to the deceiving calm, let us begin to perceive the whispers. Beneath that blanket of cosmic quietude, there lies an unimaginable reservoir of energy, vast beyond our terrestrial comprehension. It's like observing a giant ancient glacier. It appears utterly motionless, a frozen colossus, yet within its depths, titanic forces are slowly, relentlessly at work, carving valleys, grinding mountains, shaping landscapes over millennia. Similarly, the universe, in its grand silent ballet, operates on scales of energy and time that dwarf anything we experience in our daily lives. These energies aren't noisy. They don't roar or rumble in a way we can hear. Instead, they manifest as fundamental forces, the relentless embrace of gravity, the furious dance of nuclear forces, the pervasive hum of electromagnetism. These are the hidden currents, the deep rivers of cosmic energy that flow silently through everything, shaping stars, forging elements, and governing the fate of galaxies. Consider for a moment the seemingly gentle glow of a star, any star, even our own sun. What appears as a calm, steady light is in fact the product of an ongoing, incredibly violent process. Nuclear fusion. In its core, immense pressure and staggering temperatures force atomic nuclei to merge, creating heavier elements and releasing colossal amounts of energy in the process. Each second, our sun converts millions of tons of matter into pure energy, radiating it outwards as light and heat. This is not an explosion in the traditional sense, not a sudden, uncontrolled burst. Rather, it is a sustained, contained fusion reaction, a continuous, silent detonation occurring at its heart. The energy unleashed is so vast that it takes hundreds of thousands of years for a single photon, a particle of light, to zigzag its way from the sun's core to its surface, before embarking on its 8-minute journey to Earth. This immense output of energy, responsible for sustaining life on our planet, is just one whisper of the hidden power of the cosmos. And what about gravity? This invisible force, so familiar yet so mysterious, operates across truly immense scales. It is gravity that pulls together scattered dust and gas to form stars and planets. It is gravity that binds billions of stars into magnificent galaxies. It is gravity that binds billions of stars into magnificent galaxies. It is gravity that orchestrates the collisions and mergers of these vast stellar islands, events that unfold over hundreds of millions of years, releasing energies that defy human imagination. When two galaxies spiral into each other, as our own Milky Way is destined to do with Andromeda in a few billion years, it's not a head-on crash in the way two cars might collide. Rather, it's a slow, gravitational embrace, a dance of tidal forces that stretches and reshapes both structures, flinging stars into new orbits and triggering bursts of star formation. The energy involved in such cosmic mergers is staggering, silently reshaping the very fabric of the galactic landscape. Then there are the more exotic whispers, like the enigmatic dark energy, which appears to be accelerating the expansion of the universe itself. This isn't an explosion, but a subtle, pervasive push, an unseen force that is slowly, yet relentlessly, stretching the cosmic canvas, pulling galaxies further and further apart. Its true nature remains one of the greatest mysteries in cosmology, a powerful, silent driver of the universe's ultimate destiny. All these forces, these immense reservoirs of energy, exist within that initial quietude we contemplated. They are not loud, not boisterous in our human perception. They are the deep, underlying currents, the immense forces that shape everything we see and don't see, operating with a silent majesty that hums just beneath the surface of our awareness. They are the prelude, the quiet and profound foundation upon which the most spectacular and dramatic events of the universe unfold, setting the stage for something truly profound, something rarely seen, something that will soon transform a gentle giant into the ultimate cosmic fireworks. Having sensed the subtle hum of cosmic power hidden beneath the quiet, we now turn our gaze towards the most dramatic of these expressions, the ultimate grand finale for a star. A farewell so spectacular, it redefines the very meaning of explosion. We are speaking, of course, of cosmic death, yet in the universe, death is rarely an ending. More often it is a violent, necessary rebirth, a shattering that sows the seeds for future creation. And among these stellar swan songs, there is one that stands out, a crescendo of destruction and creation, the hypernova. Imagine, if you will, the slow, graceful dance of a star through its immense life, perhaps for millions of years tirelessly fusing elements in its core, radiating light and warmth. But for the most massive of these celestial giants, their lives are not destined to fade gently into the night. Instead, they are destined for a magnificent, terrifying, and utterly beautiful exit. We are not talking about a simple stellar demise, like a star peacefully exhausting its fuel and shrinking into a white dwarf, or even the familiar, brilliant burst of a standard supernova. No, a hypernova is something altogether more intense, more focused, more devastating. It is the cosmic equivalent of a single deafening clap of thunder from a sky that had only ever whispered. It is the universe clearing its throat with an incomparable roar. When a star, truly immense in its proportions, tens, even hundreds of times the mass of our own sun, reaches the end of its life, its death throes are unlike anything else. Its core, no longer able to resist the inward crush of its own titanic gravity, collapses with unimaginable speed, not merely shrinking, but imploding with such ferocity that it bounces back with a violence that defies earthly understanding. But here is where the hypernova sets itself apart. Instead of an outward-spreading spherical explosion, which is what we typically associate with a supernova. A hypernova channels its dying energy into two incredibly powerful, narrowly focused jets of matter and radiation, lasting forth from its poles at nearly the speed of light. Think of it not as a firework exploding in all directions, but as a colossal cosmic lighthouse beam, two searing shafts of pure energy piercing through the fabric of space. These jets are the signature of a hypernova, the telltale sign of a final, hyper-violent goodbye. They are the source of what we detect as gamma-ray bursts, the most energetic phenomena in the known universe. Flashes of light so intense that for a fleeting moment, they can outshine entire galaxies. This immense burst of energy is not just a destructive force. In a strange cosmic twist of fate, this unparalleled violence is also a profound act of creation. These explosions are responsible for forging and scattering many of the heavier elements, like gold, platinum, and uranium, that are essential building blocks for planets, for life itself. Without these spectacular stellar deaths, the universe would be a much simpler, less interesting place, devoid of the very materials that make up you, me, and everything around us. You know this. These explosions are responsible for forging and scattering many of the heavier elements, like gold, platinum, and uranium, that are essential building blocks for planets, for life itself. So as we prepare to dive deeper into the mechanics of this ultimate explosion, remember that it is a story of destruction, yes, but also of radical transformation, of a cosmic crescendo that echoes with both a terrifying finality and a promise of new beginnings. It is the universe's grandest, most violent farewell, forever etching its mark on the tapestry of existence, a truly profound and captivating event. To truly appreciate the ferocity of a hypernova, we must first understand the gentle, almost dreamlike beginnings of the stars themselves, those luminous behemoths that eventually meet such a dramatic end. Imagine, if you will, vast swirling clouds of gas and dust, stretching for light years across the emptiness of space. These aren't the neat, fluffy clouds we see drifting in our sky. These are immense, tenuous nebulae, cosmic nurseries composed primarily of hydrogen and helium, laced with microscopic grains of dust, the scattered remnants of long-dead stars. In these colossal, dark, and seemingly still clouds, the journey of a star quietly begins. There's no dramatic ignition, no sudden flash. Instead, it's a slow, almost imperceptible process, driven by the most fundamental force in the cosmos, gravity. Think of it like a gentle whisper in a vast, silent hall. Within these enormous clouds, there are always slight variations in density. Perhaps a distant supernova shockwave nudged a region, or simply the inherent quantum fluctuations of matter caused a tiny clump to become ever so slightly denser than its surroundings. Whatever the initial trigger, once a small region has accumulated just a little more mass, its gravitational pull subtly increases. And this is where the magic begins. That slightly denser clump begins to very, very gently, almost imperceptibly, draw in the surrounding gas and dust. It's a slow, patient accumulation, like building a cosmic snowball. As more and more material is drawn in, the clump grows, and as it grows, its gravitational pull strengthens, accelerating the process. It's a positive feedback loop, a slow, inevitable march towards concentration. Over vast stretches of time, perhaps hundreds of thousands, or even millions of years, this contracting clump of gas and dust grows larger and larger, becoming denser and hotter at its core. As the individual particles are pulled closer together, they collide more frequently and with greater energy, causing the temperature within the core to steadily rise. This contracting, warming mass is known as a protostar, a star in its infancy, still cloaked in the veil of the very cloud from which it was born. It's not yet a true star. It doesn't yet glow with its own internal nuclear fire. Instead, it radiates a dim reddish light from the heat generated by its gravitational collapse. It's a moment of profound transformation, the universe slowly knitting together raw ingredients into something spectacular. This gentle inward pull, this slow gathering of cosmic material, continues until a critical point is reached. The pressure and temperature within the protostar's core becomes so immense, so utterly staggering, that something extraordinary happens. Nuclear fusion ignites. The hydrogen atoms, squashed together under unfathomable pressure and superheated to millions of degrees, begin to fuse, combining to form helium atoms. This process releases an enormous burst of energy, pushing outwards and finally counteracting the inward pull of gravity. At this precise moment, the star is truly born. It ceases its collapse and settles into a stable equilibrium, a delicate balance between the crushing force of gravity trying to pull it inward and the outward pressure generated by its nuclear furnace. This is the main sequence phase of a star's life, a period of sustained brilliant light and warmth, a beacon ignited from the dust and dreams of the cosmos. The Sun, our own star, has been in this stable phase for about 4.6 billion years, a testament to the powerful, yet subtle, forces that bring these majestic cosmic forges to life. From seemingly empty space, a star is born, glowing steadily, patiently, ready for its long journey. To truly grasp the scale and intensity of a hypernova, it's helpful to first ground ourselves in the familiar. Let us turn our attention, gently, to our own Sun, that brilliant golden orb that warms our days and nourishes all life on Earth. The Sun is, in every sense, a star, a magnificent, glowing ball of superheated gas, a cosmic furnace tirelessly performing its work. It is, however, a rather average star in the grand cosmic scheme, a comfortable, middle-aged star that has been shining steadily for about 4.6 billion years and will continue to do so for another 5 billion years or so. Its steady, life-giving hum is a beacon in our local cosmic neighborhood, the very heart of our solar system. Think of the Sun not as a distant, abstract object, but as the closest, most powerful example of a star that we can study and feel. Its warmth on your skin, the light that paints the world in vibrant hues. These are direct manifestations of the nuclear processes occurring deep within its core. At the Sun's heart, temperatures soar to an unimaginable 15 million degrees Celsius, and pressures are so immense that matter is compressed to a density far greater than lead. In these extreme conditions, hydrogen atoms are crushed together with such force that they fuse, combining to form helium. This process, known as nuclear fusion, releases an astonishing amount of energy, which slowly makes its way from the core to the Sun's surface, taking tens of thousands of years to do so, before radiating outward into space as sunlight. Every second, the Sun converts about 4 million tons of its own mass into pure energy. Imagine that, 4 million tons gone, transformed into the light and heat that bathes our planet. Yet, despite this colossal expenditure, the Sun is so incredibly massive that it has enough hydrogen fuel to keep burning steadily for billions of years. It exists in a delicate, exquisite balance. The immense inward pull of its own gravity is perfectly counteracted by the outward pressure generated by the continuous nuclear fusion in its core. This equilibrium is what makes the Sun a stable, reliable source of light and warmth, providing the consistent conditions necessary for life to flourish on Earth. It is a stable, persistent fire, not a sudden explosive burst. The Sun is a yellow dwarf star, relatively small compared to the cosmic giants we'll soon discuss, but its presence utterly defines our existence. It drives Earth's weather patterns, powers photosynthesis in plants, and ultimately provides the energy for every living thing on our planet. It is our anchor, our fundamental source of energy, and its gentle, unwavering glow is a constant reminder of the incredible power that can be contained within a single star. Its story is one of steady brilliance, a cosmic engine of life, operating with quiet efficiency. It's a star that, in its maturity, has found its rhythm, a comforting presence in the vastness. It offers us a baseline, a familiar point of reference, against which the truly extraordinary, fleeting, and devastating events of a hypernova can be more fully appreciated. The Sun's steady hum allows us to live, to wonder, and to contemplate the more violent, yet equally fundamental, processes occurring in the distant reaches of the cosmos. Having taken a moment to appreciate our Sun, let us now gently trace the broader journey of stars, from their ethereal birth to their inevitable, varied ends. It's a cosmic life cycle, a grand narrative written in light and gravity, and understanding its various paths helps us comprehend the rarity and extremity of a hypernova. Imagine a cosmic tapestry woven from gas and dust, and each star is a thread spun into existence, glowing for a time, and then dissolving back into the cosmic loom to be rewoven into something new. Every star begins its life in a nebula, as we discussed, slowly gathering itself under gravity's patient hand. Once its core ignites with nuclear fusion, pushing outward against gravity's embrace, it enters its main sequence phase, a long, stable period where it burns hydrogen into helium. This is the longest stage of a star's life, the period of its youth and adulthood, during which it shines most consistently. Our Sun, as we just contemplated, is comfortably within this phase. For billions of years, these stars are like steady cosmic lanterns, patiently radiating energy into the vastness. However, no star burns forever. The hydrogen fuel in its core is finite, and eventually, after eons of tireless work, it begins to run low. What happens next depends almost entirely on the star's initial mass. For stars like our Sun, when the core runs out of hydrogen, it begins to contract and heat up. This causes the outer layers of the star to expand dramatically, cooling as they do so, transforming the star into a red giant. Our Sun, in about 5 billion years, will expand to such an extent that it will engulf Mercury, Venus, and possibly even Earth. It's a majestic, though for us, destructive transformation. After this red giant phase, the star will gently shed its outer layers, forming a beautiful ethereal planetary nebula, a glowing shell of gas surrounding a tiny, incredibly dense remnant, a white dwarf. This white dwarf is the cooling ember of a once vibrant star, slowly fading into eternal darkness. This is the gentle, quiet exit for most stars, a long, drawn-out sigh. But for stars born with much greater mass, their story takes a different, far more dramatic turn. These are the giants, the true titans of the stellar nursery, born with perhaps 10, 20, or even 100 times the mass of our Sun. Their lives are short, but incredibly brilliant. Into Nerine, they burn through their nuclear fuel at an astonishing rate, like a colossal candle burning at both ends. Their internal fires rage hotter, their outward pressures are immense, and their lives are measured in mere millions of years, not billions. When these massive stars exhaust their core hydrogen, they don't just expand into red giants, they become red supergiants, swelling to truly gargantuan proportions, sometimes larger than the orbit of Jupiter. And then, their final act approaches. Unlike smaller stars that gracefully shed their layers, these massive stars are destined for a far more violent, spectacular demise. When their core iron fuel runs out, for these giants can fuse elements all the way up to iron, there's no more outward pressure to resist gravity's relentless inward pull. The core collapses in a fraction of a second, triggering a monumental explosion known as a supernova, briefly outshining an entire galaxy. What remains after such an event can be either an incredibly dense neutron star, or, if the star was truly colossal, a black hole, a region of space-time from which nothing, not even light, can escape. This is the general trajectory of a massive star's death. But for a very specific, rare subset of the most massive stars, their supernova is not merely brilliant. It is an ultra-energetic hypernova, the most extreme and devastating farewell imaginable. A cosmic phenomenon that leaves behind a unique signature of pure, focused power. It's a path taken by only the most regal and robust of celestial beings, a final, unparalleled roar before eternal silence. Now, let us delve into the realm of the truly colossal, the titans of the celestial sphere, massive stars. These are not merely large, they are gargantuan, immense beyond easy comprehension. Stars that dwarf our own Sun in every conceivable way. Imagine a sphere so vast that if placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, perhaps even Saturn. We're talking about stars that begin their lives with at least 8 times the mass of our Sun and often much, much more, 20, 50, even 100 or more solar masses. It's their sheer mind-boggling scale that sets them on a unique and ultimately dramatic path, making them the likely progenitors of the hypernova. Think about the largest things you can picture in your everyday life: a mountain, a continent, even an entire planet, like Jupiter, which could comfortably swallow over 1,000 Earths. These are still minuscule compared to even the smallest of the massive stars. These stars are literally cosmic behemoths, holding within their colossal envelopes the equivalent of millions upon millions of Earth's worth of matter. Their vastness isn't just about volume, it's about the immense quantity of material, the sheer gravitational weight of all that gas and plasma. This tremendous mass is the key, the fundamental ingredient that determines their spectacular fate. It means that the gravitational forces at play within their cores are exponentially greater than those in smaller stars. The crushing pressure, the searing temperatures needed to counteract this immense inward pull are simply staggering. These stars are not just physically large, they are also intrinsically brilliant because of their immense mass. Their cores are under extreme pressure and temperature, forcing nuclear fusion to occur at an accelerated, furious pace. They burn through their fuel reserves at an astonishing rate, emitting prodigious amounts of light and energy. They are often blue or blue-white in color, indicating their intensely hot surface temperatures, far hotter than our yellow sun. They blaze with a magnificent, almost defiant radiance, dominating their immediate surroundings, outshining hundreds, even thousands, of smaller stars. When you look up at the night sky and see the brightest, most prominent stars, chances are many of them are massive stars, even if they are incredibly far away. Their sheer luminosity allows them to be seen across vast interstellar distances. But their very brilliance is a double-edged sword, tied directly to their mass. It's like a colossal bonfire. The more fuel you pile on, the hotter and brighter it burns, but the faster it consumes its resources. These cosmic titans live fast, fueled by their colossal gravitational potential, and consequently, they die young. While our sun will live for 10 billion years, a massive star might exist for only a few million years, a mere blink of an eye in cosmic time. Their lives are a magnificent sprint, a breathtaking display of raw power, a cosmic race against time. They are the true heavyweights of the universe, destined for the most extreme of endings, yet also playing a crucial role in the universe's ongoing story, paving the way for the elements that make up everything around us. Their existence, though fleeting, is essential, and their final bow is the most spectacular curtain call the universe can offer, a truly unforgettable performance by the titans of the sky. Having marveled at the sheer scale of these massive stars, we now turn to a profound paradox. These titans of the cosmos, so grand and powerful, are destined for lives astonishingly brief compared to their smaller counterparts. They are the cosmic sprinters, burning fiercely and fading quickly, a stark contrast to the slow, steady endurance of a star like our sun. Imagine a magnificent, gigantic candle, perhaps as tall as a skyscraper, but with a wick so thick and a flame so immense that it consumes its wax at an utterly alarming rate. This is the essence of a massive star's existence, a life lived too fast. The reason for this accelerated lifespan lies directly in their immense mass. As we discussed, a star maintains its stability through a delicate balance between the inward crush of gravity and the outward push of energy generated by nuclear fusion in its core. For a massive star, the gravitational pull is enormous, almost overwhelming. To resist this titanic compression, the star must generate an equally immense outward pressure. And how does it do this? By fusing hydrogen into helium in its core at an incredibly furious, almost frantic pace. The hotter the core, the faster the fusion reactions occur, releasing more energy to push back against gravity. Think of it like a giant engine. A small car engine sips fuel slowly, lasting for many years. But a colossal, high-performance racing engine, designed for maximum power and speed, gulps fuel down at an astonishing rate. Massive stars are those high-performance cosmic engines. Their cores are far hotter and denser than the sun's, driving fusion reactions that are millions of times more intense. They are not merely burning hydrogen, they are devouring it. While our sun will slowly consume its hydrogen fuel over billions of years, a star 20 times more massive will exhaust its core hydrogen in a mere few million years, perhaps 10 to 20 million years at most. This is a cosmic blink of an eye, considering the universe has existed for 13.8 billion years. This rapid consumption of fuel means that massive stars spend a relatively short time on the main sequence, their stable, hydrogen-burning phase. They are born, they blaze with incredible brilliance for a brief cosmic instant, and then they quickly move through subsequent stages of stellar evolution, fusing heavier and heavier elements in their cores. Their lives are a cascade of rapid changes from hydrogen fusion to helium fusion, then carbon, oxygen, neon, magnesium, silicon, and finally iron. Each successive fusion stage requires higher temperatures and pressures and yields less energy, and each stage is exponentially shorter than the last. The hydrogen burning phase lasts millions of years, the helium burning phase only hundreds of thousands, and the final, silicon burning phase that creates iron in the core might last for only a single day, or even just hours, before the inevitable collapse. So, while these stars are the true luminaries of the galaxy, visible across vast distances due to their sheer brilliance, their time in the spotlight is fleeting. They are the cosmic rock stars burning brightly and quickly, destined for a magnificent early exit. So while these stars are the true luminaries of the galaxy, their brevity, however, does not diminish their importance. In fact, it is this very rapid, intense life cycle that makes them so crucial to the universe's chemical evolution and sets the stage for their dramatic final act, the ultimate, most violent goodbye, known as the hypernova. Their short but spectacular lives are a testament to the powerful, relentless forces at play within the cosmos, a cosmic sprint that culminates in an unparalleled explosion. As we gently contemplate the fleeting yet brilliant lives of these massive stars, we arrive at one of their most profound contributions to the universe, their role as the ultimate cosmic factories. Far from being merely transient light sources, these giants are the universe's alchemists, tirelessly forging the very elements that make up planets, the air we breathe, the water we drink, and indeed every atom in our own bodies. Before their grand explosive finale, they perform an indispensable service, enriching the cosmos with the ingredients necessary for complexity, for diversity, and ultimately, for life. Recall that stars begin their lives primarily composed of hydrogen and helium, the lightest elements created in the Big Bang. Our sun, for instance, is busy fusing hydrogen into helium, but massive stars, with their incredibly hot and dense cores, push this process much, much further. As they exhaust their core hydrogen, their cores contract and heat even more, allowing them to ignite the fusion of helium into carbon and oxygen. Then, as the helium supply dwindles, the core contracts further, becoming hotter and denser still, allowing carbon to fuse into neon, and then neon into magnesium and oxygen. This process continues, like a series of nested Russian dolls, with each new fusion stage requiring progressively higher temperatures and pressures, and each stage occurring in a new, hotter, deeper layer of the star. Imagine the star developing an onion-like structure, an outer layer still burning hydrogen into helium, a layer beneath that burning helium into carbon and oxygen, then a layer burning carbon into neon, and so on, all the way down to the core. In the very heart of these stellar giants, temperatures reach hundreds of millions, even billions of degrees. Under these unimaginable conditions, elements like silicon fuse to form iron. This relentless cycle of fusion builds up heavier and heavier elements within the star's core. These aren't just obscure scientific elements. They are the fundamental components of our world, the carbon in our DNA, the oxygen in our atmosphere, the silicon in rocks, the iron in our blood. Without these massive stars, these elements would remain locked away, never to be dispersed into the wider universe. However, the creation of iron marks a critical turning point, a cosmic cul-de-sac. Fusing lighter elements into heavier ones releases energy, which is what powers a star and pushes outward against gravity. But fusing iron into anything heavier actually requires energy rather than releasing it. This means that once the star's core is predominantly iron, the nuclear furnace that has supported the star for millions of years suddenly ceases to produce the outward pressure needed to resist the inexorable pull of gravity. The star has effectively run out of usable fuel. So, while these stars are living, they are busily, silently, and magnificently producing the very atoms that form the basis of everything complex in the cosmos. They are giant, self-sustaining nuclear reactors, humming with the creation of the elements from which new worlds will someday form. And it is this very process of heavy element creation that sets the stage for their spectacular final act. For when the iron core inevitably collapses, it's not just a star dying, it's the contents of a vast cosmic factory being violently scattered across the universe. These heavy elements, forged in the heart of a dying giant, will be blasted out into space, mingling with pristine gas clouds, ready to become part of the next generation of stars, planets, and perhaps even life itself. This is the profound, beautiful irony of stellar death. It is the ultimate act of cosmic creation, scattering the seeds for all that is yet to come. We arrive now at the pivotal moment in the life of a massive star, the quiet tipping point that precedes an unimaginable cosmic cataclysm. Having spent millions of years fusing lighter elements into heavier ones, building layer upon layer of increasingly complex atoms in its core, the star finally faces its ultimate challenge. The fuel is running out. Specifically, its core has become a dense hot ball of iron, and iron, unlike all the elements that came before it, is a cosmic dead end. Imagine a grand ancient furnace, painstakingly tended for ages, its flames roaring, sustained by a steady supply of fuel. This furnace is the star's core, and its fuel has been hydrogen, then helium, carbon, oxygen, and silicon. Each time a lighter fuel was exhausted, the core would contract and heat up, igniting the next, heavier fuel, momentarily restoring the balance between gravity's inward crush and the outward pressure from fusion. This was the star's stable dance, a delicate gravitational ballet. But now, in the very heart of this immense star, there is only iron. As we briefly touched upon, fusing iron atoms together does not release energy, it consumes energy. This fundamental truth of nuclear physics means that the star's primary engine, its core furnace, has just sputtered out. There is no longer a source of outward pressure being generated from the core to counteract the colossal, incessant inward pull of gravity. Suddenly, the delicate balance that sustained the star for millions of years is irrevocably broken. Think of it like a perfectly balanced scale, where one side represents gravity and the other side represents the outward pressure of nuclear fusion. For the star's entire life, these two sides have been perfectly level. But now, the fusion side has vanished, leaving gravity unchecked, free to exert its immense, unyielding force without resistance. The star, in essence, loses its internal support structure. The outer layers of the star, still incredibly massive, are no longer held up by the energetic outward push from the core. They begin to fall inward, slowly at first perhaps, but then with gathering speed, like an enormous building whose central pillars have suddenly crumbled. This inward movement is not gentle, it's an inexorable, destructive gravitational collapse. The sheer weight of the star's outer layers, combined with the already dense iron core, creates an unimaginable gravitational squeeze. The core begins to collapse on itself with truly astounding speed, accelerating as it shrinks. This moment is swift, occurring in a fraction of a second, almost too fast for our minds to fully grasp. The inner regions of the star, feeling the loss of core pressure, implode, rushing inward at a significant fraction of the speed of light. The temperature and density in the collapsing core skyrocket to levels beyond anything we can replicate on Earth. Protons and electrons are squeezed together with such force that they literally merge, overcoming their natural repulsion and transforming into neutrons. The iron core is rapidly compressed into an incredibly dense ball of neutrons, a state of matter so extreme It's almost beyond imagination. This is the quiet tipping point, the point of no return. From this single, silent instant of fuel exhaustion, the stage is set for the universe's most spectacular and deadly explosion, a cosmic crescendo born from the sudden, unchecked triumph of gravity. Following the exhaustion of nuclear fuel in the core, the colossal dance of gravity takes center stage, beginning a silent, relentless victory as the star's core implodes inward under its own immense weight. Imagine a cosmic game of tug-of-war, where for millions of years, the outward pressure from nuclear fusion has perfectly matched the inward pull of gravity. Now, one team, the fusion, has suddenly and completely dropped its rope. The other team, gravity, exerts its full, unyielding force, pulling everything inward without resistance. This inward pull is not merely a gentle contraction, it is a catastrophic collapse, happening at speeds that defy our everyday experience. Think of it like a colossal, invisible hand squeezing the very heart of the star. The core, once a bustling reactor, now becomes a gravitational trap. As the outer layers of the star, which still contain a significant fraction of its total mass, begin to fall inward, their combined weight presses down on the already dense core with unimaginable force. This is not a slow, stately descent. The core collapses in on itself in a mere fraction of a second, sometimes as little as a quarter of a second. To visualize this, imagine an object the size of the Earth, but containing several times the mass of our Sun, being crushed down to the size of a city, all in the blink of an eye. The speeds involved are truly astronomical, reaching many tens of thousands of kilometers per second. As this happens, the density within the collapsing core becomes astronomical to normal matter, which is mostly empty space with tiny electrons orbiting a nucleus, is obliterated. The electrons are forced into the protons, overcoming the fundamental forces that usually keep them apart, turning them into neutrons and releasing a flood of neutrinos. This process is called neutronization. The core literally becomes a giant atomic nucleus, composed almost entirely of neutrons, packed together so tightly that there are no empty spaces between them. A single cubic centimeter of this neutron material would weigh billions of tons. If you could hold a sugar cube made of neutron star material, it would weigh more than all the cars on Earth combined. If you could hold a tree, this is a phase of profound, almost incomprehensible compression. The inward pull of gravity is so immense that it is literally ripping apart the very structure of atoms. The star's core is being squashed to the absolute theoretical limit of matter density. There is nothing left to compress, nothing left to give way. The force is so overwhelming that it defies the very laws of electron degeneracy pressure, which normally prevents smaller stars from collapsing further. This relentless inward pull is like a cosmic black hole in miniature, forming at the very center of the star, consuming itself from within. This moment of extreme compression is crucial. It is the culmination of gravity's triumph, a profound cosmic contraction that sets the stage for the dramatic rebound. All the energy that was once pushing outward is now being violently redirected inward, accumulating into an almost infinite potential for release. The profound silence of space belies this immense silent struggle at the star's heart. The inward pull is building to an unbearable tension, a cosmic spring being wound tighter and tighter, ready to snap back with unimaginable power, transforming a whisper into a roar that will echo across galaxies. Having witnessed gravity's relentless, quiet victory as the core collapses inward, we now stand at the precipice of a cosmic transformation. The moment that whisper of implosion becomes an unimaginable roar. While no sound, in our terrestrial sense, will ever emanate from this event, the energetic output will be louder than anything we can conceive. This is the moment when the universe's ultimate spring, wound impossibly tight, finally snaps back, unleashing the energy accumulated during the core's catastrophic collapse. Imagine the core, now compressed to densities that defy human comprehension. A mass several times that of our Sun crammed into a sphere, the size of a small city, composed almost entirely of neutrons. At this incredible density, The very fabric of matter resists further compression. It's like squeezing a colossal, unimaginably strong rubber ball. You can push and push, but eventually it reaches a point where it simply cannot be compressed any further. At this theoretical limit, the material in the core becomes incredibly stiff, incompressible. And this is where the rebound begins. The infiling outer layers of the star, still hurtling inward at astonishing speeds, suddenly encounter this rigid, neutron-dense core. They slam into it not like water hitting a sponge, but like a hammer hitting an anvil. The shock is instantaneous and immense. The tremendous kinetic energy of the infiling material, combined with the extreme pressures within the neutron core, causes a sudden violent rebound. The inner core essentially bounces, sending a colossal pressure wave, a nascent shock wave, ripping violently outwards. This shock wave is the universe's answer to gravity's final embrace. It is a super powerful ripple, a wave of energy and matter, blasting outwards from the newly formed neutron star or nascent black hole, in the case of a hypernova. But this shockwave faces a formidable challenge, as it propagates outward through the star's remaining, still infalling outer layers. It often loses energy. Think of it like a stone thrown into a thick, muddy pond. The ripples quickly lose their power. For most supernovae, this initial shockwave manages to blast through the star's outer layers, ejecting them into space in a brilliant, more or less spherical explosion. But for the most massive stars, especially those destined for a hypernova, the situation is even more precarious. The sheer density and mass of the infiling outer layers can be so immense that they choke the initial shockwave, preventing it from fully exploding the star from within. However, even if the initial spherical shockwave falters, the tremendous pressure and energy are still building. This quiet inward collapse has created a central engine of unparalleled power, a pressure cooker on a cosmic scale. The core has absorbed all that crushing gravitational energy, and now it seeks release. The transition from an almost silent gravitational implosion to the birth of this immense shockwave is the moment the whisper begins to gather its voice, transforming into an unheard yet universally felt roar. This is the precise moment when the stage is set for the most devastating explosion in the universe, a silent blast that will tear through the star, leaving an indelible mark on the cosmos and radiating its fury across unimaginable distances. As the star's core compresses beyond all recognition, squeezing matter into an unimaginably dense state, a neutron star or the nascent seed of a black hole, we encounter a phenomenon that seems to defy logic, an implosion's echo. This is the critical moment where the destructive inward collapse gives way to a powerful constructive outward surge. Imagine compressing a giant cosmic spring with forces so immense that it bends space-time itself. You push and push, the tension building, until it can yield no more. At that absolute limit, the spring recoils with a violence equal to the force that compressed it. This is precisely what happens in the heart of a dying massive star. The infalling matter from the star's outer layers, plummeting inward at a significant fraction of the speed of light, encounters this newly formed, super-dense core. This core is no longer compressible. It acts as an impenetrable, rigid wall. The collision is not merely a bump, it's a colossal cosmic rebound, an explosion from the inside out, yet born of an inward collapse. The kinetic energy of the infalling material, now suddenly brought to a halt, is converted into a colossal pressure wave. This pressure wave, known as a shock wave, doesn't just dissipate. Instead, it is launched outward with incredible force, propagating back through the still infalling material of the star. This is the true echo of the implosion. The energy that drove the core inward is now spectacularly redirected outward. Think of a giant wave crashing against a shore and then surging back out, pulling everything with it. This shockwave is precisely that, a wave of extreme pressure and heat, propagating outwards from the newly formed stellar remnant. It's a fundamental process, converting gravitational potential energy into kinetic energy, and then into thermal and radiative energy. The temperatures within this shockwave are so extreme that they briefly reignite nuclear fusion, forging even more elements in a fleeting, violent burst, elements even heavier than iron, such as gold and uranium, which are too energy-intensive to be created in the star's normal burning phases. The challenge for this nascent shockwave, however, is immense. As it pushes outward, it has to fight against the relentless, continued infall of the star's outer layers. It's like trying to push your way upstream against a raging torrent. The shockwave loses energy as it plows through the dense, infalling material. For many massive stars, this shockwave successfully propagates all the way to the star's surface, resulting in a typical core collapse supernova, a brilliant spherical explosion that scatters the star's outer layers across space. This is the common fate. But in the case of the truly gigantic stars that lead to hypernova, this initial spherical shockwave often stalls. The mass of the overlying material is simply too great, the inward pull too strong. The shockwave can lose so much energy that it grinds to a halt, or at least significantly weakens, before it can fully blow apart the star. This moment of potential failure, this internal struggle, leads to an even more exotic and powerful outcome. It's the point where the universe, having performed its profound act of compression, now channels its recoil into something far more focused and spectacular. The implosion's echo, instead of fading, finds a new, terrifyingly efficient way to escape, a silent, internal explosion building towards an outward surge of unimaginable power. Following the implosion's recoil, we now witness the dramatic outward surge, the birth of the shockwave that will ultimately rip apart the star. Imagine a colossal, invisible slingshot pulled taut by the immense force of gravity during the core's collapse. Now, released, it unleashes a concentrated burst of energy, pushing violently outward from the newly formed superdense heart of the dying star. This is where the star truly begins to explode. As the inward rushing material slams into the incompressible neutron core, it doesn't just stop. The kinetic energy of this cosmic impact is converted into a colossal pressure wave, a wave of intensely heated, highly compressed matter. This is the shock wave, and it begins its violent journey outward through the remaining layers of the star. Think of it not as a gentle ripple, but as an enormous supersonic bulldozer, smashing its way through everything in its path. Its leading edge heats and ionizes the stellar material it encounters, ripping apart atoms and accelerating particles to incredible speeds. This outward surge is incredibly powerful. Energy contained within this nascent shockwave is staggering, equivalent to the total energy output of our Sun over its entire 10 billion-year lifespan, released in a matter of seconds. It's an almost incomprehensible amount of power, driven by the most fundamental forces of the universe. As this shockwave propagates, it is not a smooth, laminar flow. Instead, it's turbulent and violent, carving out a path through the dense stellar material. It effectively creates a massive, expanding bubble of hot, high-pressure plasma within the star. However, as we briefly noted, the journey of this shockwave is not without its challenges. For many massive stars, the initial spherical shockwave often stalls or weakens considerably as it tries to push through the immense still-infalling outer layers of the star. It's like trying to inflate a balloon inside a rapidly deflating, incredibly heavy sack. The shockwave struggles to overcome the weight and density of the overlying material. In a standard supernova, complex processes, often involving the flood of neutrinos produced during the core collapse, manage to re-energize the shockwave, allowing it to eventually break free and burst through the stellar surface. But in the case of the most massive stars, those destined for a hypernova, this initial shockwave often doesn't make it. It falters, unable to muster enough energy to completely blow off the star's outer layers in a uniform, spherical explosion. This might seem like a failure, a dud explosion. Yet, paradoxically, it is this very failure that sets the stage for something even more spectacular and focused. When the shockwave stalls, the intense pressures and the rapid rotation of the massive star's core can lead to the formation of a black hole at the center. This nascent black hole then becomes an engine for something new. it begins to accrete the infalling material, forming a swirling disk around it. And from this disk, powerful, narrow jets of energy and matter are launched. So, while the initial outward surge of the spherical shockwave might struggle, the immense forces at play are still seeking an outlet. The energy is still there, ready to be unleashed. This stalled shockwave is merely a prelude, a redirection of power, leading to the formation of a central engine that will funnel that colossal energy into something far more concentrated and devastating. This transition from a general outward surge to a focused, powerful beam is the key difference that elevates a standard supernova to the rare and magnificent spectacle of a hypernova tearing through the star in an entirely unique manner. Having seen the initial outward surge, we now witness the crucial, violent process of this shockwave tearing through the star, a prelude to the final, magnificent catastrophe. Imagine, if you will, a colossal, invisible spear thrust from the heart of the star, pushing through layers of superheated gas and plasma, tearing a path towards the surface. This is the shockwave, its journey outwards determining the very nature of the star's explosive death. In a typical core collapse supernova, this shockwave expands more or less spherically, like a rapidly inflating balloon within the star. It blasts through the various onion layers we discussed earlier: silicon, oxygen, carbon, helium, hydrogen, successively heating, accelerating, and tearing apart these outer envelopes. As it travels, it liberates the heavy elements forged in the star's core, mixing them with the lighter elements in the outer layers. The journey is incredibly fast. What might seem like a vast distance to us within the star is traversed in mere seconds or minutes by this supersonic wave. As the shockwave reaches the star's surface, it causes a sudden, dramatic brightening, the initial breakout flash of the supernova, marking the beginning of its brilliant, fleeting peak. The star's outer layers are then ejected into space at incredible velocities, forming a rapidly expanding cloud of gas and dust that will persist for thousands of years, eventually mingling with the interstellar medium. However, as we've hinted, the story is more complex for the most massive stars, the progenitors of hypernovae. For these giants, the spherical shockwave often struggles to break free. The amount of overlying mass is simply too great, the inward gravitational pull too relentless. Tiu, Seriki, it's as if the star itself is too heavy to blow apart in a uniform manner. The shockwave might stall or significantly weaken before it reaches the surface. This failure of the initial spherical shockwave is not the end of the story. Rather, it's the beginning of a different, even more dramatic chapter. When the spherical shockwave falters, the core continues its intense gravitational squeeze. But instead of simply stopping, a new phenomenon can occur, particularly if the star was rapidly rotating. The intense pressure and gravitational forces within the collapsing core, combined with the star's spin, can cause the central region to collapse directly into a black hole. This newly formed black hole then becomes the true engine of the hypernova. As matter from the inner stellar layers continues to fall onto this nascent black hole, it forms a rapidly swirling accretion disk around it, a superheated cosmic vortex. From the poles of this accretion disk, incredibly powerful, collimated jets of energy and matter are launched. These jets are not the diffuse spherical explosion of a typical supernova. Instead, they are narrow, highly energetic beams, traveling at speeds incredibly close to the speed of light. These are the true spears tearing through the star. They bore through the still collapsing outer layers, focusing all the available energy into two opposite directions. Unlike the spherical shockwave, which had to push against the entire star's mass, these jets find a path of least resistance, carving out escape tunnels. As they punch through the stellar material, they create a colossal release of gamma rays, leading to the phenomenon we call a gamma ray burst. So, the star isn't merely exploding, it's being pierced from within by these twin cosmic drills, leaving behind a unique and powerful signature of its final, most devastating act. This internal rending is the dramatic prelude to the most luminous events in the universe. Before we plunge into the extraordinary realm of the hypernova, let us gently pause to understand its more common, though still utterly spectacular, cousin, the standard core collapse supernova. This is the brilliant stellar burst, the majestic and familiar way in which most massive stars conclude their lives, illuminating galaxies with their final incandescent breath. Imagine a star, perhaps 10 to 20 times the mass of our Sun, having lived its magnificent, though relatively brief, life. Its nuclear fuel has run its course, and its iron core has collapsed, triggering that powerful rebound and shockwave we just discussed. In a typical core collapse supernova, this shockwave successfully propagates outward through all the star's remaining layers. Oh, it's a furious, rapid event. As the shockwave rips through the stellar material, it heats it to unimaginable temperatures, causing the outer layers of the star to rapidly expand. The shockwave breaks out from the star's surface, unleashing a tremendous burst of light and high-energy radiation. This initial flash marks the official beginning of the supernova event, and within days, the entire star can brighten to incredible luminosity, outshining an entire galaxy for a few weeks or months. Think of it as a single incredibly bright light bulb in a city suddenly outshining every other light combined. The amount of energy released in a supernova is truly staggering. It's equivalent to what our Sun will produce over its entire 10 billion year lifetime, but released in a matter of seconds to minutes. Most of this energy is carried away not by visible light, but by neutrinos, tiny, ghostly particles that interact hardly at all with matter. Billions of these neutrinos pass through your body every second, silently, harmlessly, most of them originating from our Sun. But during a supernova, a flood of these neutrinos, perhaps 1,000 trillion of them, are released in a colossal burst, carrying away nearly all the energy from the core collapse. If a supernova were to occur close enough to Earth, this neutrino burst would be the first thing we'd detect, long before the light even arrived. The visible light we observe from a supernova is produced as the shockwave heats and expands the star's outer layers. These layers are ejected into space at velocities reaching tens of thousands of kilometers per second. This expanding cloud of superheated gas and dust, rich in the heavy elements forged in the star's core, and during the explosion itself, is called a supernova remnant. These remnants, like the famous Crab Nebula, can glow for thousands of years, slowly expanding and mixing with the interstellar medium. They are the cosmic recycling plants, distributing the vital ingredients for future stars, planets, and life. What remains after this standard stellar burst is typically either a neutron star, an incredibly dense remnant the size of a city, or, if the progenitor star was slightly more massive, a black hole. The key characteristic of a standard core collapse supernova is its largely spherical, or at least broadly isotropic, explosion. The energy is distributed more or less evenly in all directions. This is the more common, though still awe-inspiring, way for a massive star to say its final goodbye, a brilliant, transient beacon in the cosmic night, but still just a precursor to the true focused fury of a hypernova. Now, having considered the more common, magnificent supernova, let us turn our attention to the crucial difference, the missing link that elevates a standard stellar burst into the truly exceptional and more powerful hypernova, the formation of incredibly powerful focused outward jets. In a typical supernova, the energy is distributed fairly uniformly in all directions, a grand spherical fireball. But for a hypernova, something entirely different happens, something that channels the star's dying fury into a precise, devastating beam. Recall that for the most massive stars, the initial spherical shockwave, generated by the core's rebound, often struggles or even stalls as it tries to push through the immense overlying layers of the star. It's like trying to ignite a damp firework. The explosion might be muffled or simply fail to fully erupt. This is where the story diverges dramatically. Instead of a general explosion, the forces at play become much more intricate and directed. The key to understanding this redirection lies in two crucial factors: the extreme mass of the progenitor star and its rapid rotation. When the incredibly massive core of such a star collapses, it doesn't just form a neutron star. It's so massive that it collapses directly into a black hole. This newly formed black hole is the engine, the missing link that transforms a failing supernova into a hypernova. But it's not the black hole itself that explodes. Rather, it's the material that falls onto the black hole. As the remaining inner layers of the star continue to fall inward, they don't plunge directly into the black hole. Instead, if the star was rotating rapidly before its collapse, and many massive stars do rotate very quickly, this infalling matter forms a superheated, rapidly swirling disk around the black hole, much like water swirling down a drain, but at speeds approaching the speed of light. This is known as an accretion disk. The friction and intense gravitational forces within this disk heat the matter to extreme temperatures, creating a colossal amount of energy. It's from the poles of this rapidly spinning accretion disk that the outward jets are launched. The exact mechanism by which these jets are formed is still an area of active research, but it's believed that powerful magnetic fields, twisted and amplified by the rapidly rotating black hole and the accretion disk, play a crucial role. These magnetic fields act like cosmic funnels, collimating or focusing the immense energy and plasma into two incredibly narrow, highly energetic beams that blast away from the poles of the system, perpendicular to the disk. Think of it like squeezing a balloon that has a hole at the top and bottom. Instead of the air escaping evenly from all sides, it's forced out in concentrated streams. These jets are not just streams of gas. They are composed of matter accelerated to nearly the speed of light, carrying immense amounts of energy in the form of gamma rays and other high-energy particles. They are so powerful that they bore through the remaining stellar material, punching clear through the star and erupting into space. This outward jet, this focused fury, is the distinctive signature of a hypernova, the missing link that connects these most powerful stellar explosions to the brightest events in the universe, gamma-ray bursts. It's a spectacular redirection of power, turning a star on the brink of an ordinary death into a cosmic beacon of unparalleled intensity. We now envision a star hovering on the brink of an extraordinary fate, a final dramatic act that goes beyond even the most brilliant supernova. This is a star in its ultimate death throes, a cosmic giant that, having already run out of its nuclear fuel and undergone core collapse, now faces a choice of final destinies. But for this specific magnificent titan, its tremendous mass and perhaps a rapid spin are pushing it towards something far more extreme. A hypernova. Imagine a colossal ancient structure, its foundations crumbling, its internal fires extinguished, teetering on the edge of complete and utter structural failure. But this isn't just any collapse. It's a collapse that will unleash a focused fury. This star, having already spent millions of years fusing its lighter elements into heavier ones, culminating in an inert iron core, is now experiencing the unstoppable gravitational infall. Its core has likely already collapsed into a neutron star, and perhaps even crossed the threshold to become a nascent black hole. The initial shockwave in this particular cosmic scenario has faltered, unable to fully blow apart the star from within. The core is still collapsing, still drawing in material, and the inner layers of the star are still falling onto this incredibly dense central remnant. This moment is one of immense internal struggle, a cosmic battle between the crushing force of gravity and the desperate attempt of the star's remaining material to find an outlet for its stored energy. The star isn't merely dying, it's wrestling with the very fabric of space-time, seeking the most efficient and violent way to release the colossal energy locked within its rapidly collapsing core. It's like an immense, overpressurized boiler, seeking the path of least resistance for its explosive release. What makes this particular star different, what sets it on the path to a hypernova, is a combination of its gargantuan initial mass and, crucially, its rapid rotation. Massive stars are often born spinning rapidly, a remnant of the turbulent, swirling gas cloud from which they formed. As such a star loses mass during its life, and its core collapses, its rotation can speed up dramatically, just like an ice skater pulling in their arms to spin faster. This rapid spin, combined with the immense gravity of the newly forming black hole at its center, creates the conditions for the channeling of energy. The infalling material, instead of plunging directly into the black hole, swirls around it, forming that superheated, rapidly rotating accretion disk. This disk becomes a powerful engine, extracting rotational energy from the black hole and converting it into outgoing jets. These jets are the star's last, most potent expression, its final scream. They don't explode uniformly. They pierce through the star, like cosmic drills, focusing all their destructive power into narrow beams. So, this star on the brink isn't just about to explode. It's about to unleash a directed, unprecedented torrent of energy, a cosmic laser beam of devastation that will etch its signature across the universe. It's a rare, almost unique kind of stellar death, where the energy is not merely released but channeled, leading to a peculiar and profound spectacle. This star, teetering on the edge, is about to perform its ultimate, most dramatic act, transforming its final moments into the most luminous and violent event known to science, a silent eruption that will herald the birth of the deadliest explosion in the universe. It's a fairy, it's a fairy, it's a fairy, it's a fairy. As we gently descend from the contemplation of the pre-supernova state, we arrive at the profound question of what remains after such a cataclysm. When a massive star dies in a core collapse supernova, it doesn't simply vanish. It doesn't simply vanish. Instead, its intensely compressed core leaves behind some of the most extraordinary and enigmatic objects in the universe. Cosmic leftovers so dense and extreme that they challenge our very understanding of matter. These remnants are either neutron stars, or, in the case of the truly gigantic and rapidly spinning stars that lead to hypernova, black holes. They are the ultimate cosmic compression, the universe's way of demonstrating just how much can be crammed into an impossibly small space. Imagine taking a star, many times the mass of our sun, and squeezing its entire core down to the size of a city. Remember, that is the essence of a neutron star. Or taking an even more massive core and compressing it so intensely that it creates a region of space-time from which nothing, not even light, can escape. That is a black hole. These aren't just theoretical constructs. They are observed realities, cosmic sculptures carved from the death of giants, the universe's ultimate expressions of density and gravity. They are the silent, yet incredibly powerful, monuments to stellar demise. The type of remnant left behind depends on the initial mass of the star's core and how much material is accreted back onto it during the explosion. If the core's mass is between about 1.4 and 3 times the mass of our sun, it will typically form a neutron star. This is the Chandrasekhar limit, the maximum stable mass for a white dwarf, and beyond it, matter gets squashed further. If the core mass is above this neutron star limit, and the explosion itself doesn't blow off enough material, then the core continues to collapse, forming a black hole, and that the core continues to collapse, forming a black hole. This distinction is crucial, particularly for understanding hypernovae, as the formation of a black hole is central to their powerful jet production. These cosmic leftovers are not inert. They are dynamic, often possessing extreme properties that make them fascinating subjects of study. Neutron stars, for example, are often born spinning incredibly rapidly, and their powerful magnetic fields can sweep across space, creating beams of radio waves that we detect as pulsars, cosmic lighthouses emitting precise, rhythmic pulses. Black holes, on the other hand, are the ultimate gravitational prisons, their immense gravity distorting space-time around them, creating a point of no return, known as the event horizon. While we cannot see them directly, their presence is inferred by their powerful gravitational influence on surrounding matter, often drawing in gas and dust, which heats up and emits X-rays before disappearing forever. So, when a massive star culminates its life in a supernova or a hypernova, it's not merely a grand display of light and fury, it's also a profound act of cosmic transformation, leaving behind one of these exotic remnants. These dense, compact objects are the ultimate cosmic leftovers, embodying the extreme conditions of stellar death and serving as silent witnesses to the universe's ongoing cycle of creation and destruction, forever altering the cosmic landscape with their incredible density and gravitational might. They are the ultimate compact objects, born from the most violent events imaginable. Let us now delve a little deeper into one of these remarkable cosmic leftovers, the neutron star. Imagine, if you will, taking an entire mountain and crushing it down to the size of a single sugar cube. Now, imagine taking all the cars on Earth, all the buildings, all the oceans, all the continents, and squeezing them into that same sugar cube. That's still not dense enough. A neutron star truly defies our everyday intuition about matter. It is an object where matter is squashed to an unimaginable density, a cosmic marvel where the very fabric of atoms is utterly obliterated. When a massive star's core collapses and exceeds the Chandrasekhar limit, about 1.4 times the mass of our Sun, the maximum stable mass for a white dwarf, the gravitational pressure becomes so immense that it overcomes the electron degeneracy pressure that supports a white dwarf. Electrons are forced into protons, literally combining to form neutrons. This process, called neutronization, creates a ball of almost pure neutrons. The collapse stops only when the neutrons themselves, packed shoulder to shoulder, resist further compression due to something called neutron degeneracy pressure. This is the strongest known force in the universe, short of the force that forms a black hole. The result is a neutron star, typically only about 20 kilometers, 12 miles in diameter, the size of a small city, but containing anywhere from 1.4 to about 2.5 times the mass of our entire Sun. To put that into perspective, if the Sun was shrunk to that size, it would still be a star, but one with utterly unimaginable properties. A single teaspoon of neutron star material would weigh billions of tons. It's as if you've taken the entire population of humanity and compressed them into a single grain of sand. The density is so extreme that the matter inside a neutron star is often described as being like one giant atomic nucleus. There are no individual atoms, no empty space. It's a solid sea of neutrons, with a thin crust of regular matter on the surface, and perhaps even stranger, more exotic states of matter deep within. These incredibly compact objects are not only dense, they are often born spinning at astonishing rates. As the star's massive core collapses from hundreds of thousands of kilometers down to just 20 kilometers, it conserves its angular momentum, causing it to spin incredibly fast, sometimes hundreds of times per second. Imagine a giant ice skater pulling in their arms and spinning furiously. This rapid rotation, combined with the collapse of the star's powerful magnetic field lines into a tiny, super-intense region, creates a cosmic dynamo. These rapidly spinning, highly magnetized neutron stars are called pulsars, and they emit beams of radio waves from their magnetic poles. If these beams sweep across Earth, we detect them as precise, regular pulses, like a cosmic lighthouse. The dance of density within a neutron star is a testament to the extreme physics that governs the universe. It's a bridge between the familiar world of atoms and the enigmatic realm of black holes. These objects are not merely passive remnants. They are dynamic, energetic beacons that offer us a glimpse into the most extreme conditions of matter imaginable, born from the spectacular demise of a massive star, and sometimes setting the stage for even more profound cosmic transformations when the core's mass just tips over the edge, leading to the ultimate embrace of gravity. From the extreme density of a neutron star, we now slip into an even more profound mystery, one that truly pushes the boundaries of our understanding, the black hole. Imagine a place in the universe where gravity is so overwhelmingly powerful that nothing, not even light itself, can escape its relentless embrace. This isn't a solid object you can touch, but rather a region of space-time, an unseen vortex, a cosmic prison from which there is no return. Black holes are the ultimate gravitational traps, born from the catastrophic collapse of the most massive stars, those whose cores exceed even the neutron star limit, perhaps 3 times the mass of our Sun. When such a truly immense star reaches the end of its life and its iron core collapses, the gravitational forces are simply too immense for even neutron degeneracy pressure to halt the collapse. The core continues to shrink, relentlessly, until it forms an infinitely dense point called a singularity. This singularity is a concept that challenges our physics, a point where matter is compressed to zero volume and density becomes infinite. Deadliest becomes infinite. Deadliest becomes infinite. Around this singularity forms the black hole itself, defined by its event horizon, a boundary in space-time. This event horizon is not a physical surface. It's a point of no return. Once anything, be it light, matter, or even the subtle fabric of space-time itself, crosses this boundary, it is irrevocably pulled toward the singularity, forever lost to our observable universe. The black hole is unseen, truly invisible, because light cannot escape it. You detect their presence only indirectly, by observing their profound gravitational influence on surrounding matter. Imagine a cosmic drain, as gas, dust, or even entire stars drift too close to a black hole. They are caught in its gravitational grip. This material doesn't just fall straight in. Instead, it often spirals around the black hole, forming a superheated, rapidly rotating accretion disk, much like water circling a drain. As the material in this disk spirals inward, friction and immense gravitational forces heat it to millions of degrees, causing it to emit powerful X-rays and other forms of radiation before it plunges beyond the event horizon, never to be seen again. These X-ray emissions are one of the primary ways astronomers identify and study black holes. The concept of a black hole is deeply rooted in Albert Einstein's theory of general relativity, which describes gravity not as a force, but as the curvature of space-time caused by mass and energy. A black hole represents the most extreme possible curvature, a deep well in space-time from which there is no escape. They are cosmic paradoxes, regions of absolute nothingness that contain immense mass, invisible entities that exert enormous power. For the purposes of our journey into hypernovae, the formation of a black hole in the core of a dying massive star is not just a possible outcome, it is the crucial ingredient. When such a black hole forms, especially within a rapidly spinning star, it acts as the central engine that funnels and focuses the immense energy of the star's collapse into the powerful narrow jets that define a hypernova and give rise to gamma-ray bursts. Awful, sidit-weary desrifying. These unseen vortices are not merely the end product of stellar death. They are often the very mechanism that drives the most powerful explosions in the universe, a silent, profound embrace of gravity that reshapes the cosmic landscape and unleashes unimaginable fury. Having explored the diverse fates of massive stars, from the steady hum of our sun to the extreme density of neutron stars and the enigmatic embrace of black holes, we now turn our attention to the true protagonist of our story, the hypernova. This is not just any supernova. It is a specific, rarer outcome of a massive star's death, tied to a very particular kind of collapse, a truly unique and unparalleled event in the cosmos. While all core collapse supernovae are monumental, a hypernova distinguishes itself by its sheer power, its distinct signature, and the unique mechanism that drives it. Think of it this way. A standard supernova is like a colossal fireworks display, beautiful and powerful, erupting in all directions, illuminating the night sky with a spherical burst of light. A hypernova, however, is less like a general firework and more like a cosmic laser beam, or rather two of them blasting outwards with incredible precision and intensity. The energy released in a hypernova is typically 10 to 100 times greater than that of a standard supernova. This isn't just a matter of scale, it's a fundamental difference in the way the explosion unfolds. The key to understanding the hypernova's distinct nature lies in its progenitor star and the extreme conditions within its collapsing core. While a supernova can result from a star roughly 8 to 20 times the mass of our Sun, a hypernova generally requires a star of truly gargantuan proportions, perhaps 20, 30, or even over 100 times the Sun's mass. These supermassive stars live fast and die hard, burning through their fuel at an accelerated rate, and their cores become far more massive and dense than those of typical supernova progenitors. Furthermore, a crucial element for a hypernova is rapid rotation of the original star. Most massive stars do spin, but for a hypernova, this spin needs to be significant enough to play a defining role in the collapse. When the core of such a rapidly rotating, supermassive star collapses, it doesn't just stop at forming a neutron star. Instead, the immense gravitational forces and the conservation of angular momentum cause it to collapse directly into a black hole. This newly formed, rapidly spinning black hole is the true heart of the hypernova, the engine that powers its unparalleled fury. This is what sets the hypernova apart. While a standard supernova is driven by the outward shockwave bouncing off a newly formed neutron star, a hypernova is driven by the accretion of matter onto a newly formed black hole, which then launches powerful collimated jets. The initial spherical shockwave from the core's rebound might still occur, but it often struggles to break free through the immense overlying layers of the star. It's almost as if the star is too heavy to simply blow apart spherically. This choked or stalled supernova, combined with the presence of a rapidly spinning black hole at the center, then allows the channeled energy to escape in a different, more powerful way. So, when we speak of a hypernova, we're discussing a very specific, rare, and extraordinarily powerful type of stellar death. It's a cosmic event that isn't merely a bigger bang. It's a different kind of bang. One from the most extreme conditions a dying star can offer, an event that reshapes our understanding of stellar explosions and leaves a unique, indelible mark across the vast expanse of the cosmos. To truly unravel the mechanics of the hypernova, we must introduce the leading explanation for these colossal events, the collapsar model. Imagine, if you will, a gigantic, rapidly spinning star, perhaps 30 to 100 times the mass of our Sun, reaching the end of its magnificent, albeit brief, life. Its core has run out of nuclear fuel, and gravity's relentless grip has caused it to implode. But instead of settling into a mere neutron star, the immense weight and spin cause the core to collapse further, directly forming a black hole. This, my dear listener, is the collapsar, a collapsing star that gives birth to a central black hole, which then becomes the engine of a hypernova. The collapsar model posits that the initial, spherical shockwave that typically drives a supernova struggles to blast through the immense mass of the star's outer layers. It falters, perhaps even stalls, trapping the explosive energy within the star. However, the story doesn't end there. As the inner layers of the star continue to fall inward onto the newly formed black hole, they don't simply vanish, because the original star was rapidly rotating. This infalling material doesn't plunge straight into the black hole. Instead, it spirals inwards, forming a superheated, rapidly rotating disk of gas and plasma around the black hole, an accretion disk. Think of it as a cosmic whirlpool, with matter spiraling faster and faster as it gets closer to the central drain. This accretion disk is the true powerhouse of the collapsar. The intense friction and magnetic fields within this disk heat the material to billions of degrees, converting gravitational energy into thermal energy and electromagnetic energy. This disk is incredibly energetic, radiating intensely, but more importantly, it becomes the conduit for launching those distinctive, powerful jets. The exact mechanism by which these jets are launched is still a complex area of research, but it's believed that powerful magnetic fields, twisted and amplified by the rapid rotation of both the black hole and the accretion disk, play a crucial role. These magnetic fields act like cosmic funnels, collimating or focusing the plasma and energy into two incredibly narrow, highly energetic beams that blast outward from the poles of the system, perpendicular to the disk. These jets are the signature of the collapsar model. They are not merely streams of gas. They are composed of particles accelerated to nearly the speed of light, carrying immense amounts of energy in the form of gamma rays. These jets, unlike the stalled spherical shockwave, are so powerful and focused that they bore through the remaining stellar material, punching a tunnel through the star itself. They effectively find the path of least resistance, erupting from the stellar surface and blasting into space. This dramatic breakout of the jets is what we observe as a gamma-ray burst, GRB, the most luminous events in the universe. So the collapsar model provides a coherent narrative for the extreme violence of a hypernova. A massive, rapidly rotating star collapses, forms a black hole, and then that black hole, surrounded by a swirling accretion disk, acts as a cosmic engine, channeling the star's dying energy into two incredibly powerful focused jets. It's a testament to the intricate and sometimes surprising ways in which the universe can unleash its energy, a central engine of destruction that also creates the brightest lights imaginable. This focused fury, born from an inward collapse, fundamentally distinguishes a hypernova from any other stellar explosion. Having introduced the collapsar model, we can now vividly imagine the heart of a hypernova, a scene of focused fury, where instead of an isotropic or all-directional explosion, the colossal energy is channeled into incredibly powerful narrow jets. Picture, if you will, not a magnificent spherical firework erupting in all directions, but rather a colossal cosmic drill boring two searing shafts of pure energy directly into the fabric of space. This is the essence of the hypernova's distinct nature, its unparalleled destructive power harnessed and directed. As the central black hole forms within the collapsing star, surrounded by its superheated, rapidly swirling accretion disk, the energy generated is truly immense. But instead of this energy being dissipated broadly, it is squeezed, constrained, and launched into incredibly narrow beams. Think of how a garden hose, when squeezed at the nozzle, can turn a gentle flow of water into a powerful focused jet. On a cosmic scale, magnetic fields and the immense pressure within the accretion disk perform a similar feat, channeling plasma and radiation into these tight, collimated streams. These jets are the most powerful natural accelerators in the universe. Within them, particles, primarily electrons and positrons, along with protons, are accelerated to speeds that are almost indistinguishable from the speed of light. As these high-energy particles interact with the magnetic fields and ambient matter, they emit a torrent of gamma rays, the highest energy form of light. This is why hypernovae are intrinsically linked to long-duration gamma-ray bursts, which are the brightest electromagnetic events known to occur in the universe. The fury of these jets is not merely in their speed or their composition, it's in their penetrative power. These jets are so incredibly energetic that they can bore through the remaining still collapsing outer layers of the star, punching clean through the stellar material like giant cosmic drills. They create channels of evacuated space, allowing the high-energy gamma rays to escape relatively unimpeded. This is crucial because if the gamma rays were released in a spherical burst, they would be absorbed and re-emitted at lower energies by the dense stellar material, making them much less observable. But by channeling them into jets, the hypernova ensures its ultimate luminous signature is broadcast across the universe. The duration of these jets can vary, but for long-duration gamma-ray bursts, they can last from a few seconds to several minutes, continuously blasting out immense amounts of energy. Imagine the sun's entire 10 billion-year energy output, compressed and focused into a beam for mere seconds. The implications are staggering. If one of these jets were pointed directly at a nearby planet, the consequences would be catastrophic, bathing it in a lethal flood of high-energy radiation. Fortunately, these events are rare, and the universe is vast, making a direct hit on Earth exceedingly improbable. This focused fury, this channeling of energy into twin cosmic lasers, fundamentally distinguishes the hypernova. It's a testament to the extreme conditions found in the hearts of dying massive stars, where gravity, rotation, and magnetic fields conspire to create an explosion that is not just immense, but also incredibly precise. This focused power is what allows a hypernova to truly be the deadliest explosion in the universe, an unparalleled display of cosmic might, a silent, directed roar that carves its way through the very fabric of existence. As we contemplate the focused fury of a hypernova, we arrive at its unmistakable signature, the ultimate cosmic beacon that announces its violent birth. Gamma-ray bursts, or GRBs, these are, quite simply, the brightest lights in the universe, brief, intense flashes of cosmic light that for a fleeting moment can outshine entire galaxies. Imagine, if you will, the collective brilliance of 100 billion stars, compressed into a single momentary flash, visible across billions of light years. That is the kind of unimaginable luminosity we are talking about. GRBs were first accidentally discovered in the late 1960s by satellites designed to detect secret nuclear weapons tests. They were initially a mystery, strange bursts of high-energy radiation coming from seemingly random directions in space. For decades, their origin remained one of astronomy's greatest puzzles. It wasn't until the late 1990s and early 2000s, with the launch of new sensitive X-ray and gamma-ray telescopes, that the connection between long-duration GRBs and the death of massive stars, specifically hypernovae, was firmly established. Gamma rays are the most energetic form of light in the electromagnetic spectrum, far more energetic than visible light, X-rays, or radio waves. They are produced by incredibly violent processes like nuclear reactions or the acceleration of particles to near light speed. The fact that GRBs are composed of gamma rays tells us immediately that their source must be extraordinarily powerful. Their intensity is so immense that even from billions of light years away, they can be detected by our telescopes orbiting Earth. If one were to occur within our own galaxy, even if not pointed directly at us, it would still be a truly awe-inspiring and potentially dangerous event. These bursts are incredibly short-lived. Long-duration GRBs, which are associated with hypernovae, typically last anywhere from a few seconds to a few minutes, though some can stretch for longer. This fleeting nature makes them incredibly challenging to observe. Astronomers often describe them as cosmic fireflies. They flash into existence without warning, blaze with unparalleled brilliance, and then fade away, leaving only a lingering afterglow to study. The prompt detection of a GRB requires specialized satellites orbiting Earth, constantly scanning the sky for these sudden intense flashes. The luminosity of a GRB is truly mind-boggling. During its peak, a GRB can release as much energy in a few seconds as our Sun will emit over its entire 10 billion-year lifespan. This makes them the most luminous events known in the cosmos, more powerful than any supernova, any quasar, or any other cosmic phenomenon we have yet observed. They are literally the brightest lights the universe can produce, a testament to the extreme physics at play during the death of a supermassive star. This profound brilliance is not just a spectacle, it is a vital clue. The detection of a GRB tells astronomers that somewhere, billions of light years away, a truly gigantic star has just met its end in the most spectacular and focused way possible. It is the signature of death, yes, but also a beacon that illuminates the deepest, most distant reaches of the cosmos, allowing us to peer back in time and study the universe when it was much younger. These brief, intense flashes of gamma rays are the universe's ultimate fireworks, a silent testament to the unimaginable power contained within a hypernova. Now, having appreciated the sheer luminosity of gamma-ray bursts, let us understand why they are so incredibly bright and yet so fleeting. They are not isotropic explosions, spreading light in all directions, but rather highly directed beams of energy, much like a cosmic lighthouse beam sweeping across the universe. This focused nature is what allows them to be so powerful and yet only visible to us when pointed our way. Imagine a powerful lighthouse beacon on a rocky coast. If you are standing directly in the path of its intense beam, it is incredibly bright, almost blinding. But if you are standing off to the side, even a short distance away, you might see only a faint ambient glow or nothing at all as the main beam sweeps past. Gamma-ray bursts operate on a similar principle, but on a truly cosmic scale. The immense energy released by the collapsar engine, that rapidly spinning black hole surrounded by its accretion disk, is not unleashed in a spherical explosion. Instead, it is channeled into two incredibly narrow, powerful jets that blast out from the star's poles like twin cosmic lasers. These jets are incredibly collimated, meaning their energy is tightly focused into a narrow cone. The opening angle of these jets is typically very small, perhaps only a few degrees wide. This tight focusing is what allows the hypernova to achieve such extraordinary luminosity. All that immense energy is concentrated into a narrow beam, making it appear incredibly bright to anyone unlucky, or lucky, from an observational standpoint enough to be directly in its path. If that same amount of energy was spread out spherically, it would be far too diffuse to be detected across cosmological distances. It's the difference between shining a high-powered flashlight directly into your eyes versus shining it at the ceiling. This beaming effect has crucial implications for our observations. We only detect a gamma-ray burst if one of these narrow jets happens to be pointed more or less directly toward Earth. This explains why GRBs, despite being the brightest events in the universe, are relatively rare observations. For every GRB we detect, there are likely many more that occurred, but whose jets were pointed in a different direction, away from our telescopes. It's like standing on a vast ocean and seeing only a few lighthouses, not because lighthouses are rare, but because only a few of their beams happen to sweep past your exact location at any given moment. The incredible speed of the particles within these jets, approaching 99.99% speed of light, also contributes to their extreme brightness through a phenomenon called relativistic beaming. At such speeds, the light emitted by the particles is squashed into a narrow cone in the direction of motion, making it appear even brighter to an observer in that direction. This relativistic effect further enhances the apparent luminosity of the GRB, allowing us to see these fleeting flashes from billions of light years away, peering back in time to the early universe. So, a gamma-ray burst is not merely a flash. It is a cosmic beam, a directed torrent of energy and light, revealing itself only when its powerful gaze sweeps across our cosmic neighborhood. This explains their transient nature, their incredible intensity, and the challenge and excitement of hunting for these brief, bright signals. It's a testament to the extreme, focused fury of a hypernova, projecting its final roar across the vast, silent canvas of the cosmos. While the gamma-ray burst itself is a spectacular, fleeting flash of ultra-high energy, its story doesn't end there. For astronomers, the true scientific treasure often lies in what follows the fading afterglow. Imagine a magnificent firework that briefly lights up the entire sky, then fades, but leaves behind a lingering, beautiful glow, slowly changing colors and revealing the faint outlines of the debris it created. This afterglow is what allows astronomers to study these distant, fleeting events, a lingering echo that tells us about the burst's origin and its environment. The gamma-ray emission itself, the initial prompt burst, is incredibly brief, lasting from a few seconds to a few minutes. It's too short for ground-based telescopes to respond and point quickly enough to pinpoint the exact location in the sky. This is why orbiting observatories, like the Neil Gehrels Swift Observatory, are crucial. They constantly scan the sky for GRBs, and when they detect one, they rapidly swivel to pinpoint its location and immediately alert ground-based telescopes and other space observatories. This swift response is critical because while the high-energy gamma rays fade quickly, the afterglow begins to emerge across other wavelengths of light. This afterglow is produced as the powerful jets, having punched through the star, they crash into and sweep up the gas and dust in their path, creating a colossal shockwave that radiates across the electromagnetic spectrum in X-rays, visible light, infrared, and radio waves. This afterglow is much dimmer than the initial gamma-ray burst, but it persists for much longer, hours, days, or even weeks after the initial flash. This longer duration provides astronomers with the precious time they need to study the event in detail. The light from the afterglow tells us a tremendous amount. By observing it with optical telescopes, astronomers can measure its redshift, which tells us precisely how far away the GRB occurred. This is how we know that many GRBs, and thus hypernovae, occur at truly cosmological distances, billions of light years away, often in the very early universe. This makes them powerful probes of the cosmos, at a time when it was very young. Furthermore, the spectrum of the afterglow, the specific wavelengths of light it emits or absorbs, can reveal the chemical composition of the host galaxy, the environment around the dying star, and even the properties of the intervening gas clouds between the GRB and Earth. It's like analyzing the faint residue left behind after a powerful, distant explosion, to understand everything about the event and its surroundings. The afterglow often reveals the presence of an underlying supernova, confirming the link between long-duration GRBs and the death of massive stars. As the GRB afterglow fades, the light curve often begins to resemble that of a much fainter, but still very bright, supernova. This is strong evidence that the GRB is merely the initial, extremely energetic, collimated burst from the very heart of the collapsing star, followed by the more typical, but still powerful, spherical explosion of the star's outer layers. So the afterglow is not just a beautiful celestial light show, it is the crucial storyteller, the lingering echo that allows us to piece together the entire dramatic tale of the hypernova, like cosmic detectives, gathering clues from a fleeting, distant crime scene. It's the silent narrator of the universe's most violent goodbye. As we gently expand our view from the immediate aftermath of a hypernova, we begin to perceive its profound, far-reaching impact across the cosmos. These immense explosions are not merely isolated events. They are powerful sculptors of the galactic neighborhood, influencing the formation of new stars and subtly, yet significantly, shaping the distribution of matter within galaxies. Imagine a colossal, invisible artist wielding a fiery brush, subtly altering the cosmic canvas with each stroke. When a hypernova detonates, especially within the dense star-forming regions of a galaxy, it unleashes an incredible amount of energy and high-velocity material into the surrounding interstellar medium, the vast, tenuous sea of gas and dust that permeates a galaxy. This material, ejected at immense speeds, creates powerful shockwaves that ripple outwards through the interstellar clouds. These shockwaves can have two primary effects on star formation, acting like both destroyer and creator. On one hand, the shockwave can compress existing clouds of gas and dust. Think of it like a cosmic hand squeezing a sponge. When these clouds are compressed beyond a certain point, their density increases. And this increased density can actually trigger new episodes of star formation. The shockwave essentially provides the initial push, the gentle nudge that helps a cloud overcome its internal pressure and begin to collapse under its own gravity, leading to the birth of new stars. So in a paradoxical twist, the death of one massive star can directly lead to the birth of many others. This process is crucial in spiral galaxies, where ongoing waves of star formation are observed in their arms. On the other hand, a powerful hypernova can also completely disrupt and disperse smaller, less dense clouds of gas and dust, preventing them from ever forming stars. The intense radiation and powerful winds from the explosion can effectively blow away the raw material, creating vast, empty bubbles within the galactic disk. These superbubbles can expand for hundreds, even thousands of light-years, carving out immense cavities in the interstellar medium and pushing gas and dust to their edges. This sculpting action fundamentally alters the landscape of a galaxy, creating new pathways for material to flow and new environments for future star formation. Consider also the influence on galaxy evolution. The collective effect of many supernovae and hypernovae over cosmic time can drive powerful outflows of gas from galaxies, enriching the intergalactic medium with heavy elements. These galactic winds play a crucial role in regulating the growth of galaxies, influencing how much gas is available for future star formation, and spreading the chemical ingredients for life across vast cosmic distances. Cosmic seas, the sitting with Cray, cosmic tea. These galactic winds play a crucial role in regulating the growth of galaxies, influencing how much gas is available for future star formation, and spreading the chemical ingredients for life across vast cosmic distances. These galactic winds play a crucial role in regulating the growth of galaxies, influencing how much influencing dingerwacy. They are dynamic forces, shaping the very architecture of galactic structures. So, the cosmic impact of a hypernova extends far beyond its immediate brilliant flash. It is a powerful agent of change, a cosmic sculptor that carves out voids, compresses nebula, triggers the birth of new stars, and drives the evolution of entire galaxies. It is a reminder that even the most destructive events in the universe are often inextricably linked to acts of profound creation, forever shaping the grand, silent tapestry of the cosmos. The death of a single star can reverberate for eons, reshaping the very neighborhood it once illuminated. Now, let us turn to one of the most profound and paradoxical aspects of hypernovae, their role in what can only be described as life-giving destruction. It seems counterintuitive, doesn't it? The deadliest explosion in the universe, a cataclysm of unimaginable power, is simultaneously one of the primary mechanisms for seeding the cosmos with the very ingredients necessary for life. This violent, shattering act is in essence a profound act of creation, scattering the fundamental building blocks that make up planets, the air we breathe, and indeed, every atom within our own bodies. Recall that massive stars, throughout their brief but brilliant lives, are the universe's great alchemists, tirelessly fusing lighter elements into heavier ones in their cores. They create carbon, oxygen, nitrogen, silicon, and right up to iron. These elements are absolutely vital. Carbon is the backbone of all organic molecules. Oxygen is essential for water and respiration. Nitrogen is a key component of proteins and DNA. These are the elements that make planets habitable and allow life as we know it to exist. However, as long as these elements remain locked within the star's core, they are inaccessible to the wider universe. They are trapped within that gigantic stellar furnace. This is where the destruction becomes life-giving. When a massive star ends its life in a hypernova, the sheer force of the explosion blasts these newly forged heavy elements, along with any lighter elements from the star's outer layers, out into the vastness of space. The energetic shockwaves from the hypernova act like a colossal cosmic blender, thoroughly mixing these elements and dispersing them far and wide into the interstellar medium. Imagine a giant, cosmic confetti cannon, showering the galaxy with the ingredients for new worlds. But the story doesn't end there. The incredible violence of a hypernova also allows for the creation of elements even heavier than iron, elements that cannot be forged through standard stellar fusion. Elements like gold, platinum, silver, and uranium are believed to be primarily created during the extreme conditions of a supernova or hypernova. In the fleeting moments of the core collapse and the subsequent shockwave, the immense flood of neutrinos and the extreme neutron density in the collapsing core can trigger rapid neutron capture processes, building up these rare, heavy elements. So every speck of gold in your jewelry, every atom of iron in your blood, was very likely forged in the fiery heart of a massive star and then violently dispersed by its explosive death. These dispersed elements then mingle with the existing gas and dust clouds in the galaxy. Over vast stretches of time, these enriched clouds will eventually collapse under gravity to form new generations of stars and, crucially, new planets. Our own solar system, including Earth, is a second or third generation system. The raw materials that formed our sun, our planet, and indeed ourselves were originally forged in the hearts of long-dead massive stars and then dispersed by their spectacular explosions, perhaps even by hypernovae. Without this cycle of life and death, of creation and destruction, the universe would remain a sterile, undifferentiated soup of hydrogen and helium. There would be no rocky planets, no water, no complex chemistry, no possibility for life. So, while a hypernova is indeed the deadliest explosion in the universe, it is also, in a profound and beautiful paradox, one of the most essential architects of life, scattering the very seeds of existence across the cosmic canvas. It is a silent, yet powerful reminder that even in the most violent acts, the universe often finds a way to create and sustain. As we continue our contemplation of the hypernova's cosmic reach, we arrive at its most subtle yet far-reaching influence, the distant ripple effects that can travel across vast distances, subtly affecting gas clouds, influencing the conditions for future stars, and even reaching into other galaxies. Imagine dropping a pebble into an immense still pond. The immediate splash is obvious, but the ripples extend outwards, becoming fainter and fainter, yet endlessly propagating, touching distant shores long after the initial disturbance. The primary way a hypernova creates these distant ripple effects is through its immense energy output, particularly through the propagation of its powerful shock waves and the dispersal of its energetic radiation. While the most immediate effects are on the local galactic neighborhood, the initial burst of gamma rays and subsequent X-ray afterglow can illuminate and ionize gas clouds across truly staggering distances. This light, traveling at the speed of light, can reach and affect regions far, far beyond the immediate vicinity of the explosion, changing the chemical state of distant interstellar gas, making it glow or altering its density. Consider the energetic particles, like cosmic rays, that are accelerated to near light speeds by the powerful shock waves of a supernova or hypernova. These cosmic rays are not confined to the explosion site. They travel through the magnetic fields of the galaxy, diffusing outwards, subtly influencing the pressure and temperature of the interstellar medium. While the individual impact of a single cosmic ray is tiny, the cumulative effect of these particles from countless past explosions can play a role in heating interstellar gas and influencing the conditions under which future stars might form. These are subtle, slow ripples, but over cosmic timescales, their influence is undeniable. Moreover, the vast bubbles created by the collective explosions of multiple supernovae and hypernovae within a galaxy can profoundly influence the large-scale distribution of gas. These superbubbles and galactic winds can push gas far out into the galactic halo or even into the intergalactic medium. This redistribution of matter can affect the galaxy's overall star formation rate, draining gas from regions where stars might otherwise have formed, or compressing it in other regions to trigger new star birth. It's a slow, grand choreography, driven by the echoes of immense stellar deaths. Even between galaxies, faint ripples can exist. The very heavy elements forged in hypernovae, propelled outwards at high speeds, can eventually travel beyond the boundaries of their host galaxy. These elements then enrich the intergalactic medium, that vast, almost empty space between galaxies. While incredibly dilute, this enrichment means that when new galaxies eventually form from this intergalactic gas, they already contain the basic ingredients for rocky planets and life. This means that the death of a star in one galaxy can, over billions of years, contribute to the conditions necessary for life to arise in another galaxy entirely. So, the hypernova, while intensely localized in its immediate destructive power, casts a long and profound shadow across the universe. Its energy, its matter, and its dynamic influence propagate far beyond its initial flash, creating subtle yet significant ripple effects that shape the evolution of galaxies, enrich the cosmic medium, and lay the groundwork for future generations of stars and life. It is a silent, pervasive influence, a testament to the interconnectedness of all cosmic phenomena, even those separated by unimaginable distances and eons of time. As we reflect on the incredible power of hypernovae and their far-reaching effects, we might wonder, how do we, small beings on a tiny planet, detect these distant echoes of cosmic roars? How do we listen to events that occurred billions of light-years away, long before our Earth even formed? The answer lies in the ingenious tools of modern astronomy, telescopes, both orbiting our planet and nestled on its highest peaks, tirelessly listening for these faint whispers and dazzling flashes from the universe's most violent events. Detecting gamma-ray bursts, the primary signature of hypernovae, is an immense challenge precisely because of their brief and unpredictable nature. They are truly transient events, appearing seemingly out of nowhere, blazing intensely for seconds to minutes, and then vanishing. It's like trying to catch a lightning bug flash on a moonless night in a forest that stretches forever. This requires a dedicated, vigilant watch. This vigilance is primarily maintained by specialized satellites orbiting Earth. Missions like the Fermi Gamma Ray Space Telescope, and most famously, the Neil Gehrels Swift Observatory, are designed to constantly scan the entire sky for these high-energy flashes. They have wide fields of view, like a pair of giant, always-open eyes, looking for the faintest flickers of gamma rays. When a GRB is detected, these satellites don't just record it, they immediately spring into action. Swift, for example, is famous for its rapid slewing capability, It can literally pivot its entire spacecraft within seconds to point its X-ray and UV optical telescopes at the precise location of the detected GRB. This immediate follow-up is crucial because while the gamma-ray burst itself fades almost instantly, the longer-lived X-ray and optical afterglow begins to emerge, and that's where the real scientific bounty lies. Once Swift or another satellite has pinpointed the location and begun observing the afterglow, it sends an immediate alert to astronomers and observatories around the world. This alert is often broadcast within seconds or minutes of the GRB's detection. This triggers a global fire drill among astronomers. Large ground-based optical and radio telescopes, from Chile to Hawaii to Australia, swiftly swing into action, pointing their massive mirrors and dishes at the coordinates provided. They begin observing the fading afterglow across different wavelengths of light, gathering as much data as possible before it completely fades from view. This rapid, coordinated response is essential for capturing the precious light from these fleeting events. Why is this so important? Because the afterglow, as we've discussed, carries the vital clues. By analyzing its spectrum, astronomers can determine the GRB's redshift, which tells them its distance. This allows us to map the universe's most powerful explosions across cosmic history, studying the early universe when GRBs were likely more common. The afterglow's light also reveals the properties of the host galaxy, the type of galaxy where the star died, and even the chemical composition of the gas in the very distant universe. So listening to the cosmic roar of a hypernova is a sophisticated global effort, a race against time. It involves a network of robotic eyes in space, constantly vigilant, coupled with the swift, precise actions of giant eyes on the ground. It's a testament to human ingenuity and collaboration, allowing us to capture the transient signatures of the universe's most extreme events and piece together the silent, dramatic stories of distant stellar deaths. The challenge of observing gamma-ray bursts, and thus the hypernovae that produce them, is uniquely defined by their utterly fleeting nature. Imagine trying to photograph a single brilliant flash of lightning that occurs miles away, out of a clear blue sky, lasts for only a fraction of a second, and then is gone forever. This is the magnitude of the challenge astronomers face with GRBs. They are the most luminous events in the universe, yes, but their very brevity makes them incredibly difficult to catch and study. It's a race against time, a cosmic game of hide and seek. As we discussed, the prompt gamma-ray emission itself lasts for only a few seconds to a few minutes for long-duration GRBs. This is an incredibly short window, especially considering that these events can occur anywhere in the observable universe at any moment. Traditional ground-based telescopes, with their massive structures and complex pointing mechanisms, simply cannot respond fast enough. By the time a human astronomer receives an alert and points a large telescope, the initial, most energetic flash would be long over. This is why the development of dedicated GRB hunting satellites was a game-changer. These space observatories, like Swift, are designed with wide-field gamma-ray detectors that are always scanning the entire sky. They are the first line of defense, the vigilant sentinels. When a burst occurs, the satellite's onboard computers detect the sudden surge in gamma-ray photons almost instantaneously. Crucially, these satellites are robotic. They don't need human intervention to respond. Upon detection, the spacecraft automatically calculates the burst's position in the sky, and in a marvel of engineering, rapidly repositions itself within seconds to point its X-ray and optical ultraviolet telescopes at the GRB location. This incredibly swift slewing allows them to capture the very beginning of the X-ray and optical afterglow, which is the immediate, longer-lasting emission that follows the initial gamma-ray flash. Simultaneously, the satellite sends out an immediate alert signal to a global network of ground-based observatories. This alert often takes the form of an automated email or text message, arriving on astronomers' phones and computers within tens of seconds of the burst's detection. This triggers the rapid response among the ground team. Large telescopes around the world, many of which are designed for robotic or rapid response operation, then swing into action. Their goal is to capture the optical and radio afterglow which can last for hours, days, or even weeks. This slightly longer duration allows for more detailed observations, including spectroscopy, which can unravel the chemical composition and distance of the GRB. The fleeting flash of a GRB demands an extraordinary level of technological sophistication and international collaboration. Without the ability to detect, localize, and respond within seconds or minutes, the vast majority of these profound cosmic events would remain completely unknown to us. Verstraalde seconds of CB demands a second of BDSIU. It's a constant chase, a race to capture light from the universe's most extreme moments before they vanish forever. Each successful observation is a testament to the dedication of astronomers and the ingenuity of engineers, allowing us to glimpse these incredible transient beacons and piece together the story of the universe's deepest, most violent secrets. This rapid response capability is paramount to unraveling the mysteries that these ephemeral cosmic fireworks hold. Having seen the challenges of detecting these fleeting flashes, we now turn to the true purpose of this cosmic detective work, unraveling the secrets held within each distant echo. Every gamma-ray burst, every afterglow is a precious cosmic message, a data packet sent across billions of light-years, waiting for us to decode its story. It's like finding a cryptic, ancient scroll that has traveled through time, promising to reveal profound truths about the universe's distant past. The process of unraveling these secrets begins with careful analysis of the light collected across all available wavelengths: gamma rays, X-rays, visible light, infrared, and radio waves. Each part of the electromagnetic spectrum tells a different piece of the story, like different chapters in a very long, complex book. For instance, the gamma-ray signature itself, captured by satellites like Swift and Fermi, provides immediate clues about the burst's energy and duration, which helps classify it as a long-duration GRB, linked to hypernovae, or a short-duration GRB, linked to neutron star mergers. The shape and intensity of the gamma-ray light curve, how its brightness changes over time, can also give insights into the physics of the central engine, that rapidly spinning black hole, and its accretion disk. Then comes the crucial analysis of the afterglow. The X-ray afterglow, observed by Swift, typically fades more quickly than the optical or radio afterglow, but it provides valuable information about the initial expansion of the jets into the surrounding stellar material. The visible light afterglow, captured by large ground-based telescopes, is perhaps the most informative. By taking a spectrum of this light, breaking it down into its constituent colors, much like a prism separates sunlight, astronomers can identify the chemical elements present in the gas surrounding the dying star, and even within the host galaxy itself. This is done by looking for characteristic absorption or emission lines in the spectrum, which are like cosmic barcodes for each element. Crucially, the spectrum also allows astronomers to measure the redshift of the GRB. As the universe expands, light from distant objects is stretched to longer, redder wavelengths. The more redshifted the light, the farther away the object is, and the further back in time we are looking. GRBs have been detected with the highest redshifts of any individual objects, meaning they are among the most distant and oldest phenomena we can observe, allowing us to peer back to when the universe was only a few 100 million years old. This makes them invaluable tools for studying the early universe, including the first generations of stars and galaxies. The radio afterglow, which can persist for weeks or months, provides insights into the total energy of the explosion and the density of the gas environment the jets are expanding into. By combining all these pieces of information, the gamma-ray prompt emission, the X-ray, optical, and radio afterglows, and the properties of the host galaxy, astronomers can construct a comprehensive picture of these extreme events. They can confirm the collapsar model, estimate the mass and spin of the progenitor star, and understand how these explosions enrich the cosmos. Unraveling these secrets is an ongoing journey, a collaborative effort across continents and through the depths of space. Each new GRB detection is a thrilling opportunity, pushing the boundaries of our understanding of stellar evolution, black holes, and the very structure of our universe. It is a testament to our insatiable curiosity, our silent, patient, listening to the universe's most powerful, distant echoes. As we gently reflect on the immense power of hypernovae and their associated gamma-ray bursts, a natural question arises, one that touches upon our very existence. Could such an event pose a threat to life here on Earth? It's a valid query, given the unimaginable energy released. But let us explore this theoretical danger while also taking comfort in the vastness of space and the specific nature of these cosmic behemoths. It's a cosmic near miss, a thought experiment in astronomical safety. Imagine, for a moment, a hypernova occurring relatively close to us, perhaps within our own Milky Way galaxy. If such an event were to happen, and crucially, if one of its powerful, narrow gamma-ray jets were pointed directly towards Earth, the consequences would indeed be catastrophic for our planet's biosphere. The initial burst of gamma rays would instantly strip away a significant portion of Earth's protective ozone layer, which shields us from harmful ultraviolet radiation from the sun. Without the ozone layer, our planet would be bathed in a lethal flood of UV radiation, which would sterilize the surface, killing most plant life and severely damaging or extinguishing marine ecosystems, disrupting the base of the food chain. The gamma rays themselves would create a cascade of high-energy particles and chemical reactions in the upper atmosphere, in generating nitric oxides. These chemicals would further deplete the ozone layer and also create a thick, smog-like haze, potentially blocking sunlight, triggering a gamma-ray winter that could lead to mass extinctions. The afterglow, which lasts longer, would continue to bombard Earth with X-rays and other harmful radiation, prolonging the damage. Life on the surface, particularly complex life, would face an existential threat. Only deep-sea life or organisms protected by significant shielding might survive. However, let us gently reassure ourselves with the reality of cosmic distances and probabilities. The universe, while active, is also incredibly vast. The stars capable of producing hypernovae are exceedingly rare. They are the most massive and thus the shortest-lived stars, and they make up only a tiny fraction of the stellar population. Furthermore, these stars are generally found in specific environments, massive, metal-rich, often irregular galaxies, or in the spiral arms of large galaxies, away from the quieter, more stable galactic halo where our sun resides. Crucially, even if such a star were to explode as a hypernova, the beaming effect of the gamma-ray jets means that they are highly directional. For a GRB to be truly dangerous to Earth, one of its narrow jets would need to be pointed directly at us. The probability of this occurring, given the rarity of the stars, their distribution, and the narrowness of the jets, is astronomically low. It's like winning a cosmic lottery you don't even want to enter. Estimates suggest that a dangerous GRB event might occur in our galaxy only once every few 100 million to a billion years. Given that complex life has existed on Earth for hundreds of millions of years and has survived numerous extinction events, it's a risk we've apparently navigated quite well. While a theoretical threat exists, the universe's immense scale and the specific conditions required for a direct hit make it an exceedingly improbable scenario in our immediate future. We can rest easy knowing that for all their destructive power, hypernova are distant, rare spectacles, whose fury is usually directed far from our peaceful cosmic home. It's a reminder of the power of the cosmos, but also of our relative safety within its vast embrace. As our journey into the heart of hypernovae draws to a close, we find ourselves, as is often the case in science, not at a definitive endpoint, but at the edge of new questions. For all we have learned about these colossal explosions, many mysteries still surround hypernovae and their associated gamma-ray bursts, highlighting the ongoing journey of discovery, the cosmic puzzles that continue to beckon us. The universe, in its infinite wisdom, never fully reveals all its secrets, always leaving a tantalizing trail of breadcrumbs for us to follow. One of the most significant lingering questions revolves around the exact conditions and mechanisms that reliably produce these powerful jets. While the collapsar model, involving a rapidly spinning black hole and its accretion disk, is the leading theory, the precise physics of how magnetic fields are amplified and twisted to launch and collimate these jets remains incredibly complex and is still an active area of research. How does the energy get channeled so efficiently into such narrow beams? What are the exact roles of stellar rotation, magnetic fields, and neutrino heating in determining whether a massive star produces a standard supernova or transforms into a hypernova? These are intricate dances of fundamental forces that we are still working to fully choreograph. Another puzzle lies in the diversity of gamma-ray bursts themselves. While long-duration GRBs are strongly linked to hypernovae, there are also short-duration GRBs, which last less than 2 seconds. These are believed to arise from a different, equally violent cosmic event, the merger of two neutron stars, or perhaps a neutron star and a black hole. But are all long-duration GRBs true hypernovae? Are there some orphan GRBs that fail to produce a bright supernova afterglow? And conversely, are there some hypernovae that produce jets, but whose orientation means we never see the accompanying GRB? Disentangling these various classes and their precise progenitors is an ongoing challenge. The very environments in which GRBs occur also present interesting questions. While often found in metal-poor, star-forming galaxies, there are exceptions. How does the metallicity, the abundance of elements heavier than hydrogen and helium of the progenitor star influence its ultimate fate? This ultimate fate, do low metallicity environments, more common in the early universe, favor the rapid rotation needed for a collapsar? Studying the host galaxies of GRBs, many of which are billions of light-years away and appear as faint smudges of light, is a complex task that offers unique insights into galaxy evolution in the distant past. And then there's the question of their frequency. How often do hypernovae truly occur throughout cosmic history? While we detect a few GRBs per day, the beaming effect means we only see a small fraction of the total. Accurately estimating the true rate of these events, both locally and across the universe, is crucial for understanding their contribution to cosmic enrichment and their potential impact on life. These cosmic questions are not roadblocks, they are invitations. They are the silent challenges that drive astronomers and physicists to build better telescopes, develop more sophisticated simulations, and devise new theories. They remind us that the universe is an endless source of wonder, a tapestry woven with threads of known physics and intriguing mysteries. Each unanswered question is a promise of future discovery, a beacon guiding our exploration into the profound and tranquil depths of scientific understanding. The journey of unraveling these secrets is as captivating as the events themselves, a testament to our insatiable curiosity. As our quiet journey through the life and dramatic death of massive stars concludes, let us end with a cosmic reflection, a contemplation of these events, not just as scientific phenomena, but as part of the universe's grand, eternal cycle of creation and destruction. A hypernova, the deadliest explosion in the universe, is not merely an isolated burst of violence. It is a profound testament to the interconnectedness of all things, a silent, powerful reminder that even in the most catastrophic events, there is an inherent beauty and purpose. Imagine the universe as a vast, magnificent garden. Stars are the luminous flowers, each blooming for a time, some gently, others with furious brilliance. The hypernova is like the most dramatic pruning, a violent shattering that seems destructive, yet is fundamentally necessary for the garden's renewal and growth. The very elements that make up our world, the carbon in the trees, the oxygen in the air, the iron in the soil, the gold beneath the earth, all were forged in the fiery hearts of stars like these, and then violently expelled into the cosmos by their explosive deaths. Without the death of these cosmic titans, the universe would remain a barren, uninteresting place, a primordial soup of hydrogen and helium, incapable of forming rocky planets, water, or life. So the hypernova, in its ultimate fury, is a cosmic sower of seeds. It takes the heavy elements meticulously crafted in its core and scatters them far and wide, enriching the interstellar medium. These dispersed elements then become the raw material for the next generation of stars and planets. Our own sun is a second-generation star, enriched by the remnants of earlier stellar deaths. Our Earth, and every living thing upon it, is quite literally made of stardust. recycled through the crucible of cosmic explosions. When you look at your hand, you are gazing upon atoms that once resided in the heart of a giant star, atoms that were part of a hypernova's violent farewell. This thought, in itself, is a profound and humbling one. The cycle is endless. Gas and dust coalesce to form stars. Stars fuse elements and eventually die, returning those elements to the cosmic soup, which then forms new stars and planets. This grand ballet of creation and destruction has been unfolding for billions of years, and hypernovae are the most energetic, most dramatic punctuation marks in this eternal dance. They are the universe's way of ensuring that complexity, that diversity, that the very potential for life continues to spread and flourish. This contemplation should not stir fear, but rather a sense of deep wonder and calm. The universe is a dynamic, living entity, always changing, always transforming. These spectacular events remind us of the immense forces at play, forces that are far beyond our control, yet are intrinsically linked to our existence. They put our own lives, our own planet, into a grander, cosmic perspective. We are tiny, fleeting beings on a small blue dot, yet we are made of the same ancient stardust, connected to the universe's most violent and most creative acts. As you drift now, let this profound thought settle gently upon your mind, that even in the deadliest explosion, there is an echo of life, a promise of new beginnings. The universe, in its magnificent complexity, is both awe-inspiring and strangely comforting, a cosmic dance of light and shadow, destruction and creation, all unfolding in silent, profound majesty. Rest now, knowing you are part of this incredible ongoing story, a silent, tranquil participant in the universe's grand design. And so, my dear listener, our journey through the heart of the hypernova gently draws to a close. Perhaps the quiet power of these cosmic giants has settled in your thoughts, shifting your perspective on the grand silent cycles of creation and destruction that constantly reshape our universe. It's a reminder that even the most violent goodbyes can echo with the promise of new beginnings. I do hope you're still with me and not off exploring the far reaches of the Andromeda Galaxy in your dreams just yet. Did you happen to pick up any stray gamma rays on our journey? No? Good. Probably for the best. Did you find a sense of peace in our cosmic story tonight? If these quiet journeys bring a soft landing to your thoughts, please consider pressing that little like button or subscribing. It truly helps these tranquil explorations reach more curious minds who might also seek a quiet moment in the vastness. Your support helps keep this gentle cosmic whisper alive. May your night be filled with the soft, shimmering light of distant stars, and may your dreams be as expansive and peaceful as the universe itself. Sleep well, my friend.